Welcome back to the deep dive. If you're listening to this, you aren't looking for the surface level summary. You are likely here because you want to understand the machinery, the nuts and bolts, and the deep logic of the subject matter.
You're ready to get into the weeds.
Exactly. And today, we are going all the way to the bottom of the ocean.
It's good to be back. And you're right, today is not for the faint of heart. We have a paper that's, well, it's dense, it's geometric, and frankly, it's quite beautiful in how it ties together different dimensions of topology.
But we aren't just going to cover it.
No, we're going to inhabit it.
That's the plan. We are looking at a paper titled On the Non-Orientable 3 and 4 Genera of a Knot, Connections and Comparisons. The authors are Julia Knihs, Jeanette Patel, Thea Rugg, and Joshua M. Sabloff. And our mission today is very specific. We are going to explore a brand new mathematical quantity they've defined. It's called the Euler-normalized non-orientable genus.
It is a mouthful, certainly, but it's an incredibly powerful tool. It lets us, bridge the gap between how knots behave in three-dimensional space versus how they behave in four-dimensional space.
And just so everyone knows the drill, we are under the unabridged protocol today. That means we are not skipping the hard parts. We're going page by page, section by section, paragraph by paragraph.
Line by line.
If there's a formula, we are reading it. If there's a definition, we are unpacking it. We leave no stone unturned.
Precisely. We assume we have all the time in the world to understand this correctly. We are not rushing to the finish line. The journey is the point.
So let's start right at the beginning, the abstract.
Let's do it.
The abstract opens by telling us exactly what they're doing. The very first sentence reads, "We define the Euler-normalized non-orientable genus of a knot and show that it connects a variety of ideas in the theory of non-orientable surfaces bounded by knots."
Right. And connect is really the key word there, isn't it? Usually in knot theory, you have these invariants that work well in 3D, like the cross-cap number, and then you have different invariants that work in 4D, like the slice genus.
Right. They live in their own worlds.
Exactly. And these authors are proposing a quantity that exists in both worlds and, more importantly, allows us to compare them directly. And the non-orientable part is crucial too. We're so used to thinking about Seifert surfaces, which have a clear front and back.
The top and the bottom.
Yeah. Here, we're dealing with surfaces like Möbius strips, where you can walk from one side to the other without ever crossing an edge. One-sided surfaces.
Okay, so that brings us to the end of the first sentence of the abstract. I think we've established the premise. Have we missed any nuance there?
I think we've unpacked it fully. It's a bridge between dimensions, specifically for these one-sided surfaces. Let's move to the second sentence.
Okay. The second sentence is a bit of a list. It says, "We use this quantity to reframe non-orientable slice torus bounds on the non-orientable 4 genus to bound below the Tureyev genus as a measure of distance to an alternating knot, and to understand gaps between the 3- and 4-dimensional non-orientable genera of pretzel knots."
Oh, okay. There's a lot to unpack there. Let's take it piece by piece.
Please.
First, reframe non-orientable slice torus bounds. Okay, so a bound is essentially a limit. It's a floor or a ceiling. What's the absolute minimum complexity of a surface that a given knot can be the boundary of?
They put a number on it.
Right. A slice torus bound usually comes from comparing your knot to well-understood knots, like torus knots. But the word here is reframing. That implies that by using this new normalized genus, those old inequalities, those limits, they suddenly become much more geometric and intuitive.
So it's not just a dry number anymore.
Exactly. It becomes a measure of distance, something you can almost visualize.
Okay, next up in the list was the Tureyev genus. We'll definitely need to unpack that fully later, but for now, this is a way of measuring how far a knot is from being alternating, right?
Correct. An alternating knot is one where the diagram has crossings that go over, under in a perfect sequence. Most knots aren't like that. The Tureyev genus basically puts a number on how messy, or how non-alternating the knot is compared to that simple ideal.
And the last part of the sentence, gaps. This is about the difference between the complexity of a knot in 3D versus 4D. And they mentioned pretzel knots are the specific testing ground.
Exactly. Pretzel knots are this great family of knots that are constructed just by twisting strands together, like a pretzel. They're often used as counterexamples or test cases because you can tune their parameters very precisely to create all sorts of interesting behaviors.
Okay, that covers that beast of a second sentence. Are we satisfied with that breakdown? We've hit the 3 main applications.
I think so. We've got reframing bounds, measuring distance to alternating, and analyzing these dimensional gaps. Let's look at the final sentence of the abstract.
All right. It reads, we also define the Euler-normalized genus for essential surfaces in knot exteriors and illustrate connections to the slope conjecture.
Okay, now that's a big deal. The slope conjecture is this deep, famously difficult question that tries to link the pure geometry of the knot complement, that is, the empty space around the knot, to these algebraic quantum invariants like the Jones polynomial.
And if this new quantity touches the slope conjecture.
It means it's doing serious work. It's suggesting a fundamental link between the classical visual geometry of knots and the more abstract physics-inspired quantum side of things.
Okay, that covers the abstract entirely. It's a roadmap of where we're going. Have we missed any nuances there?
I think we've unpacked the intent nicely. We know the what, this new genus, and the why, connecting 3D and 4D, measuring complexity, and maybe even touching on quantum topology. Let's move to the introduction.
Section 1. Introduction. The first paragraph essentially restates the goal, tying all these different threads together, but they make an interesting distinction. They say they investigate this quantity to reframe the meaning of bounds, not just to prove them.
That is a subtle but really important distinction. Sometimes in math, you just want the sharpest possible inequality. You want to prove that 6 Stochels' y-axis is less than or equal to y, and that's it.
The result is the thing.
Right. But here, they want to understand the structure of that inequality. Why is it there? What geometry is forcing it to be true? They're after the story behind the numbers.
And they mention right away that the quantity vanishes on alternating knots.
Vanishes just means it equals 0. So for the simplest, most well-behaved class of knots, the alternating knots, this new Euler-normalized complexity is 0. That's a great sanity check. It confirms that it's a good measure of distance away from that simple baseline.
That covers the opening motivation. Do we feel grounded in the author's philosophy here?
Yes, I think so. The philosophy is structure over raw data. They want to understand the shape of the mathematical landscape. Let's get into the definitions.
Okay, let's get into the meat of it. Section 1.1, non-orientable genera of a knot. They start with the basic notation. Decala subset S33K is a subset of S3.
So 3S33, S3 is the three-dimensional sphere. The easiest way to think about it is just our normal 3D space, but sort of wrapped up so it's finite. It's the natural home for knots. And $T is our knot, just a closed loop floating in that space.
They define a spanning surface.
Yeah.
A compact, smooth, embedded surface, $4 subset S33Fers is a subset of S3 with partial F equals KF, the boundary of F equals K.
This is the crucial idea. The knot isn't just a piece of string, it's the edge of a piece of fabric. That fabric is the surface 5. If the fabric has a consistent front and back all the way through, it's orientable.
Like a disk.
Exactly, but if it's like a Möbius strip, where you can walk from the front to the back without crossing an edge, then it's non-orientable. That's what we're focused on here.
And with that, they define the non-orientable 3 genus, which is also called the cross-cap number. Here's the formula. Gamma 3K in mathematicians. Gamma 3 of K equals the minimum of the first Betty number of F, such that F is in script F3 of K.
Okay, let's break that down. Mathcal 3K script F3 of KS is just the set of all possible non-orientable surfaces in 3D space that have the knot dollars as their edge.
So all the possible fabrics.
All the possible fabrics. And B$F, B1 of F, is the first Betty number. Roughly speaking, you can think of B$1 as counting the number of holes or handles in the surface. It's a measure of topological complexity. So the whole formula for gamma 3 of K is asking a simple question. What is the simplest possible non-orientable surface, the one with the fewest holes, that fits inside this knot?
That paragraph sets the whole 3D stage. Anything else on the definition of gamma 3, Lar?
Just a bit of context. It was introduced by Clark back in 1978, so this is a classical invariant. It's been around for almost 50 years. This isn't a new idea, but what they do with it is.
Right, so now they pivot to the 4-dimensional shift. They define a filling, which is a surface phi dollar subset. B phi TF is a subset of B4.
So B4 is the 4-dimensional ball. Its boundary is our 3D universe, the 33S3. So now the surface isn't just floating in our space anymore. It's dipping down into the 4th dimension.
Oh, interesting. So the knot itself stays on the edge in our world.
Exactly. The knot dollar stays on the boundary in 3S, but the fabric, the surface VOS, hangs down into the interior of the 4D ball.
And the formula for the 4 genus looks almost identical. It's gamma 4K. Gamma 4K equals the minimum of the first Betty number of F, such that F is in script F4 of K.
Some idea, what is the simplest surface with the fewest holes that fills the knot if we are allowed to use this extra 4th dimension?
And they immediately note this inequality. Gamma 4K, gamma 4 of K is less than or equal to gamma 3 of K. Why is that necessarily true?
Well, because any surface that exists in 3D can just be, pushed slightly into the interior of the 4D ball. So the set of all possible 3D surfaces is a subset of the 4D surfaces. You have more options in 4D.
More room to maneuver.
Exactly. More room to potentially untangle things, to find a simpler configuration that just wasn't possible in 3D. So the minimum complexity can only go down or stay the same. It can never go up.
Okay, we've covered the distinction between spanning in 3D and filling in 4D. Are we clear on the domains?
Yes, I think so. Spanning is 3D, filling is 4D. And 4D gives you more freedom. The logic holds.
All right. They then mention some of the tools used to study this. Heegaard-Floer homology, Kovanov homology, gauge theory.
Right, and this is them signaling that we're in the deep end of the pool now. These are the heavy machinery of modern low-dimensional topology. Heegaard-Floer homology, for instance, is this incredibly powerful set of invariants that comes from looking at intersection points of shapes in high-dimensional spaces. It translates very complicated geometric information into algebra that you can actually compute.
So these are the tools you'd use to actually calculate something like gamma 4,4.
That's right. You aren't going to find the answer by just looking at the knot. You need these massive algebraic machines.
Now we get to the normal Euler number. It's written as Ife into math BVZ at F is in 2Z, the even integers.
Okay, the normal Euler number, this measures how much the normal bundle of the surface twists. Imagine you have little arrows sticking straight out of your surface perpendicular to it at every point.
Okay.
As you move around a loop on the surface, do those arrows twist around? That twisting is what EFF captures, and for these non-orientable surfaces, it's always an even integer.
They say it relates to boundary slope and pushing the interior, which I assume we'll define later. But here it is, the core definition of the paper. They call it the Euler-normalized first Betty numbers. The formula is gamma pion BF, these are called K, frac 1 2 F, capital gamma plan plus minus of F equals the first Betty number of F plus or minus the quantity, sigma of K minus 1/2 the normal Euler number of F.
Okay, this is the crown jewel. Let's really look at the components here. You have Libby dollar Libby of F, that's the raw complexity of the surface, the number of holes. You have sigma of K, which is the signature of the knot. That's a standard classical invariant. And then you have our new friend, EO dollars of F, the twisting number.
So why combine them in this very specific way?
Yeah.
With the plus minus and the 1/2?
The authors explain it perfectly with this idea of adding twisted bands, which is shown in Figure 1.
Right. They say if you take a surface and you add a twisted band to it, the Betty number, B$1, goes up by 1. But the Euler number, E of Euler, changes by exactly plus or minus 2.
Exactly. Imagine you have your surface, you take a little strap of fabric, you attach it to the surface at both ends to make a new handle, but you put a half twist in the strap before you attach the second end. You've clearly added a handle, so the Betty number B$ increases by 1, but that little half twist also changes the overall twisting of the normal bundle. It changes the $2 by exactly 2, or nax 2, depending on which way you twist. Now look at the formula for gamma, capital gamma minus. The B$ term goes up by 1. The EF dollar term goes up by 2. But it's inside the parentheses as frac u EF su minus 1/2 E of F. So that part of the expression goes down by 1.
Oh, the plus 1 and the minus 1 cancel out.
They cancel out perfectly. The value of gamma, capital gamma minus doesn't change at all.
So that's why it's Euler normalized. It's an invariant. It's specifically constructed to be invariant under this operation of adding twisted bands.
Precisely. It filters out the noise. It says, I don't care about this superficial complexity you're adding by just putting in little twists. I'm looking for something deeper, something that doesn't change when you do that. It's like looking at the signal without the static.
That is very clever.
Yeah.
So based on that key property, they give definition 1.1. They define their new invariants. The first is half in math. F in math, PF, gamma hat plus minus n of K equals the minimum of capital gamma plus minus of F, such that F is in script Fn of K.
Right, so you look at all the possible surfaces, you tabulate this invariant gamma ping capital gamma plus minus for every single one, and then you take the absolute minimum value you can find. That minimum value is the new invariant, hat gamma, gamma hat.
And they also define an average genus. Franken 1, 2, plus hat gamma K plus hat n K gamma of K equals 1/2 times the quantity gamma hat plus n of K plus gamma hat minus n of K.
Just the average of the plus and minus versions, a way to get a single number out of the two.
That feels like a very solid foundation. We've defined the key term, and crucially, we understand why it's defined that way. That was section 1.1. Have we missed any nuance there?
I think we have hit the core mechanism that invariance under twisting. That's the entire justification for the definition. It's not arbitrary, it's engineered. We can move to 1.2.
All right. Section 1.2, inspiration from geography questions. This refers to something they call Allen's geography.
Geography here is a wonderful metaphor. Imagine a map or a grid, like graph paper. On the x-axis, you plot the Euler number. On the a-axis, you plot the Betti number,
Okay.
Allen asks a simple question. For a given knot, which points, $B on this grid, can actually be created by a real surface? You can't just pick any two numbers. The set of points that are possible, that's the geography of the knot.
It's the territory of possibilities. And they define a wedge shape on this map. The formula is Vrago E2 sigma equals the set where B is greater than or equal to 1/2 the absolute value of E minus 2 sigma of K. And figure 2 helps visualize this.
Yeah, picture a sharp V shape on that graph paper. The very tip of the V sits at a specific point on the x-axis, a point determined by the knot signature, sigma of K. The key result from classical theory is that the geography, all the valid realizable surfaces, they all have to live inside or above this V shape.
It's a forbidden zone.
It is. It's a boundary. And the really cool thing is this new invariant catechan gamma hat plus minus n of K has a beautiful geometric meaning on this picture. It represents the vertical distance from any point in the geography set down to the boundary of that V shape.
So it's not just an algebraic trick anymore.
No, it's a measurement you can see on the map. It's how far above the minimum your surface is.
That helps visualize it immensely, which leads them to Theorem 1.2, relating this picture to the Heegaard floor law bound. The first part is maxi vk 0, 1 plus 4k, the maximum sigma of k minus 2 epsilon of k, and 0 is less than or equal to gamma hat plus 4 of k. And the second is similar for the minus version. The maxi vk sigma 4k, the maximum of 2 epsilon of k minus sigma of k, and 0 is less than or equal to gamma hat minus 4 of k.
Right. So if ln epsilon, which they denote here as vk epsilon of k, is a very powerful, very modern invariant from not-Flower homology. It gives us incredibly strong bounds on the 4 genus. This theorem says that their new geometric vertical distance invariant is bounded below by the difference between the classical signature sigma dollars and this modern quantum invariant variant.
It's connecting the old and the new.
It's connecting 1960s topology to 2000s topology in one clean inequality.
Okay, the geography visualization seems clear. It's a map of valid surfaces, and it's constrained by the signature. Let's do a check. Have we missed anything in section 1.2?
No, I think the wedge and the vertical distance are the key takeaways. The geometry is the point. Let's move on to 1.3.
Section 1.3, alternating knots and the Turayev genus. And this section opens with Theorem 1.3, which is a big one. It says, a knot is alternating f and d only if cat gamma plus 3k, gamma hat plus 3 of k equals 0 equals gamma hat minus 3 of k.
This is a characterization theorem, which is always a fantastic result to have. It tells you exactly what an alternating knot is through the lens of this new invariant. If both the plus and the minus normalized genera are 0, the knot is alternating. If even one of them isn't 0, it's not.
It's a perfect test.
It's a perfect test. It establishes that Angadamus gamma hat really is a measure of how non-alternating a knot is. The more non-zero it is, the further from that simple ideal you've strayed.
That is a very clean result, and it leads them directly to discussing the Turayev genus, to your vase.
Right. The Turayev genus comes from the study of the Jones polynomial. Turayev realized that for any non-alternating diagram, you can construct a special surface. And the genus of that surface, which we call GTK, G sub t of k, basically counts how many extra handles you needed to sort of fix the non-alternating parts of the diagram. It's historically very important. It was key to resolving some of the old Tate conjectures about knot diagrams.
And Theorem 1.4 connects their new invariant to it. Gamma 3kk. Gamma 3 of k is less than or equal to the Turayev genus of k.
Which says that the classical non-orientable genus, the cross-cap number, is always bounded above by this Turayev genus. It puts a ceiling on that complexity.
Then we get corollary 1.5, which gives us a specific formula for a family of torus knots that have a high Turayev genus. The formula is GTT 2k 2k1. K11 is the Turayev genus of the torus knot T of 2k, and 2k minus 1 is greater than or equal to k minus 1.
Yeah, this is just them demonstrating that the Turayev genus isn't trivial. It's not bounded by some small number. It can get arbitrarily large. As you make the knot more complex by increasing tollers, the Turayev genus grows right along with it.
And that leads to conjecture 1.6. For adequate knots, they believe that GTK, gamma 3K, G sub T of K equals gamma 3 of K.
Adequate knots are a very large, important class of knots that generalize alternating knots. They're knots whose diagrams behave nicely in a certain combinatorial sense. The authors suspect that for this entire broad class of knots, the bound from the previous theorem is actually an equality. The two measures of complexity are the same. That would be a very strong result if it's proven true.
Finally, in this section, they mention the slope conjecture again, this time citing work by Curtis and Taylor on boundary slopes and Jones polynomial degrees.
Right. We're going to see this in more detail later, I'm sure. But the slope conjecture tries to relate these geometric numbers called boundary slopes, which are basically angles that surfaces can make, to the highest and lowest powers of the variable dollars in the Jones polynomial. The fact that this paper's invariant lines up perfectly with those degrees for alternating knots suggests there are some very deep connections waiting to be fully understood.
Okay, that covers 1.3. The key here is the clean link between the Euler-normalized genus being 0 and the knot being alternating. Happy with that?
Absolutely. Let's move to 1.4, the gaps.
Section 1.4, genus gaps. And the central question is, how different can the 3D genus be from the 4D genus?
Right. We know the 4D one is smaller, but how much smaller?
Proposition 1.7 introduces a specific pretzel knot family to answer this. It's PP, PKK, RR, NaxR1, P1, MashR knots, K. And it claims three pretty shocking things. First, gamma 4P called 9A equals to double 1, gamma 4 of P equals 1. Second, gamma 3 filling equal to double 100, gamma 3 of P equals 2N. And third, G Volarani, J42, the Billerani key war of P is greater than or equal to 1/2 of K minus R minus 2.
This is huge. Let's look at what that means. The four-dimensional non-orientable genus, gamma 4P, is always tiny. It's just 1, a simple Möbius strip. But the 3D complexity, gamma 3,3, is $2, and you can make non as large as you want.
So the gap can be arbitrarily large.
Arbitrarily large. This proves there's an infinite gap between the 3D and 4D ordinary non-orientable genus. What's easy in 4D can be impossibly complex in 3D.
But then they immediately follow up by saying the Euler-normalized gap for the same family of knots is small. It's less than or equal to 2.
Right, so while a raw genus, the Betty number, diverges wildly, the normalized genus stays close together. This is strong evidence that the normalization is capturing something more fundamental, something more stable across dimensions. It sees past all that superficial 3D complexity.
But then, just to complicate things, Theorem 1.9 says we can find large gaps for the Euler-normalized genus too if we use connected sums. The formula is hat gamma jamma 3kn, nec 3kn, hat gamma hat minus 3 of kn minus gamma hat minus 4 of kn equals 2n.
So they show that even this more stable invariant can be broken apart. You can create a knot where the 3D normalized complexity is $2 while the 4D one is 0. It establishes that 3D and 4D are fundamentally different worlds. Even for this more sophisticated normalized quantity, the gap is real.
Okay, that was the intro. It really sets up the entire paper. Section 1.5 just gives the plan for the rest of the paper. So let's follow that plan and move to section 2. Spanning surfaces in 3 dimensions.
Let's do it. Time for the details.
The section 2.1. Boundary slope and 3-dimensional geography. They start by properly defining the boundary slopes. You take your knot, you push it slightly along the surface, $5 to get a new knot, and the formula is ZSF LKKK K equals the linking number of K and K prime.
Right, so imagine you have 2 copies of the knot. One is the original, the other is just shifted a tiny bit along the surface it bounds. The linking number, call dollars, just counts how many times those 2 loops wind around each other with signs. That number is the boundary slope. It's a very geometric measure of how the surface is slanted as it meets the boundary of the knot's neighborhood.
And they give a direct relation to the Euler number we've been talking about. E3F, E3 of F, E3 of F equals negative S of F.
Yep.
They show an example in figure 3, the trefoil knot bounding a Möbius strip, and calculate that T3F equals the T3SF, E3 of S equals negative 6.
This just confirms that for surfaces in 3D, our abstract twisting number, the normal Euler number, is just the negative of this very concrete, computable linking number.
They then list some properties of the Euler number. It vanishes on orientable surfaces. It's always even. And they give this important congruence relation. E3FS equiv to B1 F P mod 4, or E3 of F is congruent to S of F is congruent to 2 times B1 of F modulo 4.
This is a powerful little parity check. It puts strict constraints on which pairs of BB are even possible in our geography map. You can't just have any Euler number with any Betty number. They have to match up in this specific way modulo 4. It rules out a huge number of possibilities.
Then they formally define the 3D geography, 3D3K, as the set of all realizable pairs, E3F, B1F, and they bring back the wedge, defining it as ELEF. inequality is vol-free EB, 1/2 the absolute value of E minus E is less than or equal to B minus B. And they state that the full geography, 3D at Gallers, is the union of all these wedges.
This goes back to our discussion about the twisted bands. If you find just one surface with coordinates on our map, you can start adding twisted bands to it. Each twisted band generates a new surface. And the collection of all surfaces you can get this way forms that infinite V-shape, that wedge, sitting on top of your original point.
So the entire geography
It's just the collection of all these V-shapes, one for each base surface that you can't get from another by twisting.
Okay, completeness check on 2.1. The wedge concept and the boundary slope definition seem clear and well-motivated now.
Yes. The key idea is that one surface generates a whole infinite family via twisting, and that family creates a V-shaped wedge on our geography map.
Section 2.2, construction, state surfaces. This sounds like a way to actually build these surfaces. They start with a knot diagram, D or dollars, and talk about A resolution versus B resolution at a crossing. Figure 5 shows this. A resolution connects the regions one way, B resolution connects them the other way.
This is standard stuff from Kaufman's state sums if you've seen things like the Jones polynomial construction. At every crossing in your 2D diagram, you have a choice. You can either smooth it out horizontally, that's say the A resolution, or vertically, the B resolution.
And if you make a choice at every single crossing,
you end up with a collection of simple non-intersecting circles in the plane. This is called a state.
the next step is you fill in these circles with disks. Then you connect them with half-twisted bands where the original crossings used to be. And they mention a basic state surface is one where no band connects a circle back to itself.
Right. The basic ones are the cleanest type of surface you can build this way. If a band connects a circle to itself, it's just like adding a localized twist, which we already know how to handle with our wedge idea. The basic surfaces are the fundamental building blocks.
And this construction is powerful. Theorem 2.2 by Adams and Kindred says that for alternating knots, these state surfaces generate the entire geography. Corollary 2.3 follows up, saying the geography is just the union of the wedges that come from these basic state surfaces.
This is an incredible computational tool. It means if you want to understand the entire infinite geography of an alternating knot, you don't have to search through all possible surfaces. You just need to follow this simple recipe, find the handful of basic state surfaces, and they tell you everything. All the other infinite possibilities are generated from those few.
And they even give a formula to calculate the Euler number directly from the state. Lemma 2.4 says, E3 of S equals A S B S, B S W R D, E3 of F sub S equals A of S minus B of S minus the right of D, where 2RD is the rise of the diagram.
It's just a counting game. For a given state, single dollars, count the number of A resolutions, subtract the number of B resolutions, and then subtract the writhe of the original diagram. That number pops out, and it's your Euler number. It's that simple.
They give an example, 2.5 for the trefoil knot. The all A state gives the classic Seifert surface. And the calculation gives $2 B to $2. The all B state gives a Möbius strip, and we get 2, 6, B, B a 1. And figure 4 shows the geography grid. You can see the points at $2 and $6.
And you can see the wedges. The Möbius strip at $6, one's $1, generates a V shape of points going up from it. The Seifert surface at $2 generates another one. The union of those two V shapes is the complete map of all possible non-orientable spanning surfaces for the trefoil.
Example 2.6 does the same for the 5-2 knot. They walk through the calculation and find 3 basic surfaces.
Right. It's just showing that for more complex knots, you get more basic states, and so you get more wedges overlapping to form a more complicated geography.
Okay, completeness check on 2.2. The construction of state surfaces seems very mechanical, but it's clearly an essential tool for alternating knots.
It's the dictionary that translates from the 2D combinatorics of the diagram directly to the 3D topology of the surfaces. Very concrete, very powerful.
Section 2.3. Construction. Pinch surfaces for torus knots. So a different construction for a different family of knots. This involves something called the pinch move. They describe it for a torus knot TOPQ, Staver-Wass, where the product PPQ is even. Figure 8 shows it's a band move that connects 2 adjacent strands of the knot.
Torus knots are the ones that can be drawn without intersection on the surface of a donut. A pinch is exactly what it sounds like. You find 2 parallel strands on the donut and you pinch them together by adding a connecting band. This simplifies the knot.
It changes the parameters of the knot to new ones, transolars. The formula is $3 P2T. S equals the absolute value of P minus 2T, S equals the absolute value of Q minus 2H. And they say you can iterate this process. You keep pinching and pinching, and eventually the knot simplifies all the way down to an unknot, a TK. Then you cap that simple loop with a disk.
This is a recursive algorithm. You simplify the knot step by step until it falls apart into a simple loop. Then you fill that loop with a disk. If you trace that process backwards, undoing the pinches, you've built a specific kind of surface for your original torus knot. That's the pinch surface.
And Lemma 2.7 gives the Euler number for these surfaces. It's a very simple formula. 3 Thomas PQ E3 of F3 of P comma Q equals negative PQ.
Simple and elegant. The Euler number is just the negative product of the two torus knot parameters.
Completeness check on 2.3. The pinch move seems to be the specific construction method tailored for torus knots, just as state surfaces were for alternating knots.
Correct. It's the right tool for that specific job.
Okay, on to section 2.4. Essential surfaces. This seems like a shift in gears, they say. Not all knots have generating sets like alternating knots do, so we must look at essential surfaces.
Right. The state surface trick was great, but it really only works well for alternating knots. For a general messy knot, there's no simple diagrammatic recipe, so you have to turn to a more powerful, more general theory, and that's the theory of essential surfaces.
They give some definitions. The knot exterior is E3 set minus no, E3 set minus nu of K.
That's just the 3D space around the knot. You take the whole space and you drill out a little thickened tube around the knot. What's left over is the exterior.
The boundary slope is now a rational number, A over B in the rationals union 1 over 0. And they define compressing disks and boundary compressing disks.
These are ways a surface can be flabby or redundant. A compressing disk means your surface has a sort of bubble that you could pop to simplify it. A boundary compressing disk means it has a flap near the edge that you could smooth out.
And an essential surface is one that has neither of these.
Exactly. An essential surface is one that is pulled completely taut. It's incompressible and boundary incompressible. You can't simplify it any further without fundamentally tearing it or changing its nature. These are the rigid fundamental surfaces in the knot complement.
They then define a rational wedge, tilde DUA day, and proposition 2.10 states 3KK subset tilde to B, R3 of K is a subset of W tilde K. And they state in words, the geography is constrained by essential surfaces.
This is the critical insight of the whole section. The entire infinite geography of a knot isn't random. It is completely contained within wedges that are generated by the handful of finite, rigid, essential surfaces. If you can find the essential surfaces, you find the absolute limits of the geography.
This leads to Lemma 2.11, which looks like the technical heart of the paper. It's about bounding the change in slopes under partial compression. The main inequality is 2.3.11, the absolute value of E3 of F prime minus E3 of F is less than or equal to 2.
Right. So a partial compression, a boundary compression, is a move where you simplify a surface that isn't essential. The authors need to know, when I do this simplification, does my Euler number jump all over the place? Could it go from manic 6 to 100?
And they prove no, it can't.
Exactly. They prove it can change by at most 2. This is a crucial stability result.
The proof details look intense. They talk about intersections of an arc beta bubble on the boundary torus and use a matrix in CSL math.del2z. The final formula is vathq2 cells plus 2n plus 1q. The absolute value of S of F prime minus S of F equals the absolute value of 2 over q times the quantity 2s plus 2n plus 1 times q is less than or equal to 2.
This is hardcore geometric topology. They're using the modular group, CSL2s, which is the group of transformations of a torus, to analyze how curves can intersect on the boundary of the knot exterior. The details are technical, but the result is that the denominator of that fraction, 2s plus 1q, grows quite fast.
It forces the fraction to be small.
Very small. Specifically, less than or equal to 2. This bound is what makes their whole normalized genus idea work. If the slope could jump by 100 every time you simplified a surface, the normalization would be meaningless. This lemma guarantees it is stable.
And corollary 2.12 wraps it up. Capital gamma plus minus of F is greater than or equal to the minimum of capital gamma plus minus of F prime, such that F prime is in script F of K.
Which says, in words, that you can always simplify your surface down to an essential one, and the Euler-normalized genus will only go down or stay the same. It never goes up. So if you want to find the minimum value, the gamma neat gamma hat, you only need to look at the essential surfaces.
Completeness check on 2.4. This logic, that you can always compress down to an essential surface and that this process is controlled, seems to be the main engine for many of the proofs later on.
Absolutely. It reduces an infinite search space of all possible surfaces to a finite, manageable list of essential surfaces. It's the key theoretical tool.
Okay, we're moving to section 3. Fillings in 4 dimensions. Let's see how the story changes. Section 3.1. Normal Euler number in 4-dimensional geography. They define it using cobordisms, which are surfaces in dollars in $1 times S33.
Right. In 4D, a surface isn't just static. It connects a knot, say, k dollars at time 0 to another knot k or knot KO line at time 1. It's a history or a cobordism between them.
They give 2 equivalent definitions. The first, using a push-off, is E4 F equal cable LK and LK equal K L or F equals the linking number of K naught and K prime naught minus the linking number of K1 and K prime 1.
So it's just the difference in the linking numbers at the start and the end of the cobordism?
The second, using diagrams, is E4 F WR D0 D1 E4 of F equals the writhe of D naught minus the writhe of D1.
Same idea, but with diagram writhe.
And lemma 3.1 is reassuring. It says the 3D and 4D Euler numbers agree up to context. So E4 of F, E4 of S, E3F, Mackie SFS.
Right. This confirms we're still talking about the same fundamental quantity. The 4D definition is a natural extension of the 3D one.
The 4D geography, RKK, uses the same wedge definition as before. But then they give example 3.3, which highlights the key difference. For the trefoil knot, the 3D and 4D geographies are identical. But for the 5-2 knot, the 4D geography is strictly larger. They say the $0.2 $1 exists in 4D via a flat band move, but not in 3D.
And this is the whole crux of the 3D versus 4D difference. In 4 dimensions, you have enough room to do things like pass strands through each other at singularities or add these flat bands that would be impossible in 3D without self-intersection. This extra freedom allows you to create new surfaces to reach new points on the geography map, like the $2 and dollars, that are literally impossible to construct in 3D.
So the map of possibilities gets bigger. They show this with a Möbius strip filling in figure 10, completeness check on 3.1. The key is that 4D allows more points on the map.
Yes, the 4D geography contains the 3D geography and is often strictly larger, more room, more possibilities.
Section 3.2 is very short, just revisiting the pinch surfaces from before and extending them to the 4-ball $44. Lemma 3.4 just gives the new formula for the Euler number.
Just confirming that that construction method also works in 4D. It's bookkeeping.
Okay. Section 3.3, signature and the Gordon-Litherland bound. This looks important. They introduced the Gordon-Litherland pairing on a surface few Zeller.
Right, the GL pairing. This is a classic tool. It's a way to compute the signature of a knot sigma cobble using any spanning surface, not just a special orientable Seifert surface.
And it leads to proposition 3.5, which is the formula sigma k plus sigma k equals sigma of f plus e of f over 2.
A beautiful formula. It ties the knot's signature directly to 2 properties of the surface. The surface's own signature, a sigma, and its twisting, its Euler number, ES.
This then leads to the famous theorem 3.6, the Gordon-Litherland inequality.
Yeah.
Fractional do little 1f2, the absolute value of the quantity sigma of k minus e of f over 2 is less than or equal to b1 of f. And they say this inequality immediately implies that gamma pm4f capital gamma plus minus 4 of f is greater than or equal to 0.
This is it. This is why the Euler-normalized genus is always non-negative. If you just rearrange the terms in the Gordon-Litherland inequality, it is exactly the statement that gamma pal is greater than or equal to 0.
So our vertical distance on the geography map
Has to be positive. The geography is forced to be inside that signature wedge because of this fundamental inequality from Gordon and Litherland. It all connects.
And this brings us back to that visualization of the wedge sigma k based at the point 2 inner.
That's the V shape from the intro. This is the theorem that proves the geography must live inside it.
Okay, that covers that. Now 3.4, for us further bounds, we get theorem 3.7, which introduces another bound, this one from Heegard-Flower homology. The inequality looks similar. Frac B1, the absolute value of the quantity 2 epsilon of k minus e of f over 2 is less than or equal to B1 of f.
So now we have a second V shape. One comes from the classical signature, that's do bisma. The other comes from the modern Heegard-Flower invariant epsilon, and that defines a new wedge, WL.
And any real surface has to satisfy both inequalities.
Which means the true geography must lie inside the intersection of these 2 wedges. It's even more constrained than we thought.
Corollary 3.8 gives a known lower bound on the 4 genus. Frac gamma 4k, the absolute value of the quantity epsilon of k minus sigma of k over 2 is less than or equal to gamma 4 of k.
Right, that's a standard result, but the reframing is what's next.
Exactly. The proof of theorem 1.2 from the introduction. They say to visualize the intersection of the two wedges, as shown in figure 11, and the Euler-normalized genus is the vertical distance between the boundaries.
And it's such a great picture. Imagine two V-shapes on a graph, but their tips are at different points on the x-axis. The valid region, the geography, is the area that's above both V's. The Euler-normalized genus is just measuring how far the edge of one V is from the edge of the other, vertically. It turns a complicated algebraic inequality into a simple, beautiful picture of two overlapping cones.
Completeness check on 3.4. The geometric interpretation of the two wedges, dB sigma and nanophila, seems to be the main point here.
Yes, and the idea that their new genus is quantifying the disagreement between the classical signature invariant and the quantum upsilon invariant, it's measuring the gap between the two theories geometrically.
Fantastic.
Okay,
On to section 4. Euler-normalized genus agreements. And 4.1 is about alternating knots.
right. Time to prove that big characterization theorem from the intro.
4.1.1 gives a combinatorial proof of theorem 1.3. The goal is to show that for the all A and all B state surfaces, we get gamma plus FA equals $, and gamma FD equals $.
We want to prove that for alternating knots, this special quantity vanishes just by counting things in the diagram.
Lemma 4.1 gives the formulas for any dollars and B dollars for these state surfaces.
Mhm.
For the all A surface, EFA equals 2 CRE of F sub A equals 2 times CR minus, where CR is the number of negative crossings. And B dollar MFA equals 1 SA plus CRB1 of F sub A equals 1 minus the magnitude of S sub A plus CR, where CRA is the number of state circles.
Just counting properties directly from the diagram.
Then they bring in two more standard identities for alternating diagrams. Lemma 4.2 is a combinatorial identity, $2 is an SECR plus SA plus SBD, and Lemma 4.3 is the signature formula, sigma k, frac 12 SWRD plus SASB, sigma of k equals 1F times the quantity negative writhe of D plus magnitude of S sub A minus magnitude of S sub B.
Okay, so they're lining up all the pieces of the puzzle. They have formulas for $, and no sigma, all in terms of simple diagrammatic quantities.
And then comes the calculation. They just walk through the algebra. They plug all these formulas into the expression frac 12 and sigma rho and show that after a bunch of things cancel, it's exactly equal to sigma k.
And if that term equals sigma k, then when you plug it into the gamma plus formula, which is $B plus sigma froc 1, it becomes $B, which is $B B1. No, wait. The term is $B plus sigma froc $1, and they show WAC 1 2 E B1, so $B plus sigma. Plug that in, you get sigma plus sigma 2 sigma. Let me reread.
Let's check the formula again. Gamma plus F B1F plus sigma k gamma. They show that frac 1 2 EFA B1 B1F near k and into sigma k.
Ah, I see. So sigma k gamma. It's sigma k.
Wait,
Wait, no, I'm mixing up the terms. Let's write it out.
Yeah.
We want to show $B plus sigma frac 1 2 E. That's the same as showing sigma frac 1 2 E, and that is exactly what they prove.
There it is.
My apologies. The algebra does cancel out perfectly. QED.
No problem. That's why we're here.
Yeah.
So the combinatorial proof works. Then 4.1.2 gives a much shorter, more elegant topological proof. It uses Green's characterization, theorem 4.4, which says a knot is alternating if and only if it bounds both positive and negative definite surfaces.
Right. Joshua Green proved this incredible theorem. A knot is alternating if and only if you can find one spanning surface whose intersection form is positive definite, all positive eigenvalues, and another that's negative definite.
And how does that help?
Well, if a surface is definite, it's a known fact that the Gordon-Litherland inequality we saw earlier becomes an equality. And if it's an equality, that means the distance to the boundary of the signature wedge is 0.
Which means gamma is square is 0.
Precisely. It's a much more high-level conceptual proof than the messy combinatorial one.
Okay, completeness check on 4.1. We have two proofs, one by brute force algebra and one by high-level topology, and both confirm that gamma is 0 for alternating knots.
Exactly. The result is solid.
Section 4.2. Relation to tori of genus. They show how the tori of surface is constructed from the state circles and give the formula for the tori of genus of a diagram. GTD, freight 1, 2 plus 2 SASB, G sub T of D equals 1/2 times the quantity CR plus 2 minus magnitude of SA minus magnitude of SB.
Right. This is Torreya's construction. You take the all A state circles and lay them on a plane, say, above the all B circles, and then you connect them with saddles corresponding to the crossings. The genus of this closed surface is the tori of genus.
And the proof of theorem 1.4 is to show that this is equal to frac 1, 2 gamma plus FA plus gamma FB.
Yeah, they basically just sum up the equations we used in the combinatorial proof in 4.1. It turns out that the tori of genus is exactly the average of the positive and negative Euler-normalized genera, but for the two specific state surfaces, 5A and 5'U.
So why does that prove the inequality gamma UT2?
Because gamma 3 is the average of the minimum possible gamma values, and geometry is the average of two specific gamma values. The minimum is, by definition, less than or equal to any specific value, so the inequality has to hold.
Makes sense. Then we have section 4.3, an example with the torus not t, $4 to the 3. Proposition 4.5 gives all the numbers. The ordinary genera differ. Gamma 3 yields a 2, but gamma 4 equals no one.
So there's a gap in the ordinary genus.
But the normalized genera are gamma plus $3 and d yields 2, and they're the same in 4D. The tribe genus is G yield 1.
This is a great example. Notice that now gamma plus 3 equals dulas. This means that from the plus perspective, the knot, T $4, $3, behaves like an alternating knot. It sits right on the boundary of its signature wedge. But from the minus perspective, it's far away, with $2, 2.
And crucially, the normalized genera are the same in both 3D and 4D, even though the ordinary genera were different.
Exactly. The normalization is seeing a stability that the raw Betty number misses.
Completeness check on 4.3. They use the pinch surfaces they defined earlier to actually realize these values and do the calculation.
Yes, the calculation holds up, and it's a very illuminating example.
Section 5. Ordinary genus gaps, pretzel knots. This is where they prove that the ordinary gap can be arbitrarily large using proposition 1.7. We're looking at that family P equals a P, RNER day, $1. The proof that gamma 4 1 is really neat. They use two types of band moves. A type I move is orientable, and it simplifies the knot. A type 2 move is non-orientable, and it turns the simplified knot into the unknot.
Okay, so a band move is where you perform surgery on the knot by adding a little connecting strap. A type I move is just a standard band. It doesn't add any twists. A type 2 move is like the twisted bands we saw before. It adds a non-orientable feature.
So they do some orientable moves to clean it up, and then one final non-orientable move turns the whole thing into a simple loop.
And since they used exactly one non-orientable band in the process of turning it into the unknot, the resulting surface that fills it is a Möbius band. A Möbius band has B dollars another 1, so gamma 4 has to be 1. It's an incredibly efficient way to fill the knot in 4D.
But for the 3D genus, they just cite a result from Ichihara and Mizushima that gamma 3 is large, and they use signature bounds to show the orientable 4D-ness 243 is also large.
Right. So this specific pretzel knot is a strange beast. It's complex in 3D. It's complex if you only use orientable surfaces in 4D. But the moment you allow just one non-orientable twist, one Möbius band, it becomes simple in 4D.
And proposition 5.1 confirms that for this family, the normalized gap is small, less than or equal to 2.
Again, showing the stability of the new invariant. The ordinary gap is infinite. The normalized gap is tiny.
Completeness check on section 5. Differentiating the type I and type 2 band moves is the key to that gamma 4 and 1 over proof.
Absolutely. Type I is orientable, a regular band. Type 2 puts a twist in, making it non-orientable. That's the whole trick.
Section 6. Euler-normalized genus gaps. Slice pretzel knots. This looks like the most technically demanding section of the paper.
It is. Buckle up.
The goal is to prove that for the pretzel knot P3, the normalized 3 genus is Hakama 3 equals 2. To do this, they use Hatcher and Ortel's algorithm.
This is a classic but very heavy-duty algorithm from the 80s. Its purpose is to find and classify all the essential surfaces in the complement of certain kinds of knots, like pretzel knots. It's a machine for doing exactly what we said was necessary in section 2.4.
The process involves dividing 3 into 3 balls that meet at an axis, and then using an edge path diagram on a grid.
Right. It's a combinatorial representation of the topology. Paths on this diagram correspond to how a surface is built from fundamental pieces called saddles and tubes.
They define basic edge paths, and then 3 types of edge path systems, which correspond to the 3 ways an essential surface can be constructed.
Type A is the most complicated one. You have to solve a linear equation, lambda-dos, to make sure the sheets of the surface all match up correctly. Type 2 and 3 are more straightforward geometric constructions.
They then do the specifics for their knot, PFUA 3 Hain, and for the type I system, they find a solution $2 frac 2 in the 3n and 1 door knot equals 2n minus 2 over 3n minus 1.
So they found the specific way that the most complicated type of essential surface can exist for this knot.
Now, in 6.2, they compute the properties of these surfaces. They define metrics like length and twist, and then they have these wild formulas for the Euler characteristic. For type I, it is chi lambda, Fangstang lambda, plus n1 u0 n2 over number of lambda equals negative magnitude of lambda plus n minus 1 over 1 minus u naught times n minus 2.
That formula is a beast, but what it's doing is amazing. It's calculating a fundamental topological property, the Euler characteristic, purely from the combinatorics of the path in the diagram, and that special number $2 they just solved for. It's the dictionary between the diagram and the topology.
They then do the full calculation, which they summarize in Table 1. For the type I surface, they find that gamma frac n plus 2 gan plus 1 capital gamma minus of lambda equals n plus 2 over 2 minus 4 over n plus 1, which is always greater than or equal to 32.
And for all the other types, the type 2 and type 3 surfaces, they calculate that gamma naught is always 2 or more.
Right, so they've checked every single possibility given by the algorithm.
It's a proof by exhaustion. The lowest value they find is for the type I surface, but since the genus has to be an integer, a value of 1.5 or higher means the minimum possible integer value is 2.
And that proves proposition 1.8. Since the minimum value for any essential surface is 2, and we know from corollary 2.12 that simplification can't lower it enough, the 3D normalized genus, 2 log gamma 3,3, must be 2.
But this particular knot, P3 $3010s, is known to be a slice knot.
Meaning it bounds a smooth disk in 4D.
Correct, which means its 4D genus is 0, and therefore its normalized 4D genus, order 4, is also 0. So the value drops from 2 in 3D to 0 in 4D. There is a normalized gap of 2.
Completeness check on section 6. The edge path mechanics are incredibly intense, but the overall logic is clear. Enumerate all possible candidates using the algorithm, calculate gamma for every single one, and then find the minimum.
Precisely. It's an amazing application of a classic, powerful algorithm to answer a question about a very new invariant.
Okay, we are on the home stretch. Section 7. Euler-normalized genus gaps, connected sums. This section starts with lemma 7.1 on additivity. It says, plus 1 gamma 3 k1 plus minus 3 of k0 connects them k1 equals gamma hat plus gamma hat of k1.
This says the invariant behaves as nicely as you could possibly want. If you tie two knots together with a connected sum, the normalized complexity just adds up.
And the proof of theorem 1.9, the final big result, just puts the pieces together. They say, take the knot in dollar to be the connected sum of 9 copies of the pretzel knot we just studied, P333 teller. By the additivity lemma, the 3D normalized genus just adds up. Since each one had a genus of 2, the total is $2.
But in 4D, the connected sum of two slice knots is still a slice knot. So the 4D normalized genus is just $0 plus 0 plus S plus 0, which is $0.
And there it is. The 3D normalized genus is 2 nummels at dollars. The 4D normalized genus is 0. The gap is 2 nummels, which can be arbitrarily large.
A fantastic final result. By chaining together these special pretzel knots, you can make the gap between the 3D and 4D Euler-normalized genus as massive as you want.
And that covers the entire paper. We made it all the way from the abstract to the final theorem.
We did. We unpacked the definition, the geography, the connection to alternating knots, the pretzel knot gaps, the intense edge path calculation, and finally the connected sum construction. It's a complete story.
So final thoughts. For me, this Euler-normalized genus, it feels like finding the true way to measure the complexity of a non-orientable surface.
I completely agree. By normalizing out that twisting noise, that static, you get a quantity that respects the 4D bounds, it identifies alternating knots perfectly, and it still reveals these deep structural gaps between the dimensions. The aha moment for the whole paper is that invariance under the twisted band move. That's the core insight.
And a provocative thought to leave our listeners with. This paper repeatedly connects this very geometric invariant to the slope conjecture, and by extension to the Jones polynomial. The Jones polynomial is a quantum invariant. Essential surfaces are purely geometric objects. Could this normalization, this specific way of filtering out noise, be the missing link that helps unify quantum topology and classical geometry?
Is game gonna later grow, Ma? The Rosetta Stone.
That's the question to mull over.
Indeed.
This has been The Deep Dive. Thank you for joining us. Keep diving deep.
Welcome back to The Deep Dive. Usually we take a stack of articles, skim the cream off the top, and serve you a nice digestible latte of information. You know, give you the talking points you need for a cocktail party.
Which is great, but today's different.
Today's is very different. Today we are initiating what we're calling the unabridged protocol.
It sounds a little ominous when you say it with that reverb in your voice, but it's actually A pretty exciting experiment. It's a completely different way of consuming knowledge.
It is. The mission today is to analyze a single mathematical paper, not by summarizing it, not by skipping the hard math, but by deconstructing it. Line by line, formula by formula.
We're assuming we have infinite time.
Exactly. We have all the time in the world to understand every single nuance. We aren't just reading. We're trying to unpack the rhetorical purpose and the mathematical necessity of every single statement.
We're leaving no stone unturned.
Yeah.
I mean, if there's a variable, we have to define it. If there's a theorem, we have to ask why. If there's a lemma, we ask what breaks if we take it out.
Precisely. The paper on our desk today is titled On the Non-Orientable 3 and 4 Genera of a Knot, Connections and Comparisons. It was authored by Knihs, Jeanette Patel, Thea Rugg, and Joshua M. Sabloff. The date on the manuscript is February 16th, 2026.
So a very recent contribution to the field of low-dimensional topology. And it's tackling a really fundamental question, which is the relationship between how complex a knot is in our standard three-dimensional world versus how complex it is if you have access to the fourth dimension.
So are you ready to engage the protocol?
I am ready. Let's open the document.
We begin, as all papers do, with the abstract. The first sentence reads, "We define a new quantity, the Euler-normalized non-orientable genus, to connect a variety of ideas in the theory of non-orientable surfaces bounded by knots."
Okay, let's pause immediately. Right there. This is the thesis statement. They're introducing a new quantity.
Yeah.
And in mathematics, you don't just invent quantities for fun. You do it because the current tools aren't measuring something specific enough, and they call it Euler-normalized.
I want to dig into that term, Euler-normalized. I know Euler usually points to the Euler characteristic, faces minus edges plus vertices. But here, are we normalizing for size or, shape?
Not exactly size. Think more about twisting. Euler here is referring to the Euler number, or more specifically, the normal Euler class. It's a measure of how much a surface twists around itself in the space it's living in. So normalized suggests they are adjusting the standard measurement, the genus, or complexity of a surface to account for this twisting.
So they're trying to create a stable metric in what could be a really chaotic environment.
That's the idea. And they specify non-orientable surfaces.
Right. Which is crucial.
It is. Most people, when they think of surfaces, they think of a sheet of paper or a sphere. Those are orientable. You have a distinct up and a distinct down. If you put an ant on top, it stays on top. A non-orientable surface is like a Möbius strip.
The classic example.
Exactly. If you walk along a Möbius strip, you eventually end up on the other side without ever crossing an edge. There's no up or down. There's only one side.
Right.
This paper is obsessed with those twisted, one-sided surfaces that are bounded by a knot.
Okay, so the next sentence in the abstract says, "This quantity is used to reframe non-orientable slice torus bounds on the non-orientable 4 genus to bound below the Topology genus as a measure of distance to an alternating knot, and to understand gaps between the 3 and 4-dimensional non-orientable genera of pretzel knots."
Whoa, that is a dense sentence. We absolutely need to break that into 3 distinct claims.
Okay, claim 1.
First, slice torus bounds. In 4-dimensional topology, we often try to bound the complexity of a surface using these things called invariants. They're saying this new quantity makes those bounds make more sense. It reframes them.
It's like putting on a new pair of glasses where the blurry bounds suddenly come into focus.
That's a great way to put it. Okay, second claim. Bound below the Topology genus.
Yeah.
The Topology genus is a measure of how far a knot is from being alternating. An alternating knot is sort of the simplest kind to draw over, under.
Yeah, very regular.
Very regular. If a knot isn't alternating, its Topology genus is greater than 0. So the authors are claiming their new math gives a hard floor, a lower limit for this measure of complexity.
And the third claim, understand gaps between the 3 and 4-dimensional non-orientable genera.
This is the geometric heart of the paper. A knot lives in 3D space. You can fill it with a surface in 3D, but you can also view that 3D space as the boundary of a 4D ball and fill the knot with a surface inside that 4th dimension.
And usually the 4D surface is simpler, right?
It can be, because you have more room to maneuver.
An extra direction to move in.
Exactly. The gap is the difference in complexity between the best 3D surface and the best 4D surface. And they're using this new tool to measure that gap specifically for a family called pretzel knots.
Okay, final sentence of the abstract. Further, we make connections to essential surfaces in knot complements and the slope conjecture.
Okay, essential surfaces. These are surfaces that sit in the empty space around the knot and can't be compressed or simplified any further.
So they're like the skeleton of the space.
They're the rigid structural skeleton of the knot's complement. That's a perfect description. Connecting a new genus definition to these rigid surfaces implies a very deep structural link. It's not just about the knot, it's about the space around the knot.
Okay, let's do our first completeness check. I'm looking at the abstract again. We've talked about the new quantity, sliced torus bounds, triad genus, gaps, and the slope conjecture. Have we missed any nuances here?
I think we've thoroughly unpacked it. The mission parameters are set. We know what they're trying to do. Let's turn the page.
Section 1, Introduction, Paragraph 1. This paper seeks to tie together several threads in the theory of non-orientable surfaces bounded by knots, using a new quantity called the Euler-normalized non-orientable genus of a knot.
They're reiterating the mission. And that metaphor, tying together threads, I'm almost certain that's a deliberate pun, given we're doing knot theory.
Has to be. Okay, next sentence. This quantity has both 3- and 4-dimensional versions. We investigate this quantity in several settings. First, we reframe the meaning of non-orientable sliced torus bounds on the non-orientable 4 genus.
Just confirming the roadmap, nothing new there.
Second, we show that the quantity vanishes on alternating knots and, in fact, yields a lower bound on the toriad genus.
Okay, that phrase, vanishes on alternating knots, is a crucial test for any new invariant. If you apply a complexity meter to the simple case, which here are the alternating knots,
And it reads 0.
and it reads 0, that's a very good sign. It means your meter is calibrated correctly. It's measuring complexity relative to that baseline.
Finally, we use it to understand gaps between the 3- and 4-dimensional non-orientable genus for pretzel knots and connected sums. Along the way, we will suggest connections to essential surfaces, the Colored-Jones polynomial, and the slope conjecture.
Ah, they added Colored-Jones polynomial here, which wasn't explicitly in the abstract. That's interesting. It connects this very geometric topological story to quantum invariance, which is a whole other beast. But generally, this paragraph sets the stage.
Okay, completeness check on the first paragraph of the introduction. Are we good?
We've covered the scope and the specific mathematical objects they plan to touch. I think we're ready to proceed to the next sentence, which is the start of subsection 1.1.
Subsection 1.1, non-orientable genera of a knot. And here comes the math. To define the Euler-normalized non-orientable genera of a knot, Gauler's subset S3-3K is a subset of S3. We begin by setting notation.
Standard setup. Dollars is our knot. 3s33 is the 3-sphere.
Stop. We have to do this. S3. Most listeners, when they hear sphere, they think of a basketball, the surface of a ball. But mathematicians say 3-sphere. What is the difference? Why is that important?
It's a great question. A standard basketball is a 2-sphere. Its surface is two-dimensional. You can move up, down, or left, right on its surface. The 3-sphere, or 3s33 door, is the surface of a ball that lives in 4-dimensional space. Now, that's hard to visualize. So a better way to think about it, for our purposes, is that it's our entire 3-dimensional universe, plus a single point at infinity that closes it all up.
So it's a finite wraparound 3D space.
Exactly. The knot is just floating around in this finite universe.
Got it. Okay. A compact, smooth embedded surface $5 subset S330 is a subset of S3 with partial f equal k. The boundary of f is equal to k is a spanning surface of dollars.
This is the soap film analogy. Visualize a wire loop, like one you'd use for blowing bubbles.
Mm-hmm.
That wire loop at the knot, dollars. When you dip it in soap solution, the soap film that forms inside the loop is the surface, $5. It spans the knot. The mathematical condition, partial f k shade s, just means the edge of the soap film is exactly the wire loop itself.
Makes sense. Okay, next up. Let mathcal 3k script f3 of k be the set of all spanning surfaces of dollars. Define the non-orientable 3 genus or cross-cap number of be the gamma 3k and Mackey f3k, gamma 3 of k, equals the minimum of d1 of f, such that f is in script f3 of k.
Okay, let's deconstruct that formula. Gamma 3k is the metric we're defining. To calculate it, we look at the set of all possible surfaces that span the knot. That's Mathio 3k. For each one of those surfaces, we calculate a number, $b$f2.
Right. And what is $b$f2?
It's the first Betty number. It's, roughly speaking, a count of the number of holes or tunnels in the surface. A disk has $b$1 a cylinder. A cylinder, or an annulus, has one hole, so $b$1 on all ordinals. A Möbius strip also has one essential loop, so its $b$ is also 1.
I see.
So the formula says, find the simplest possible non-orientable surface, the one with the fewest holes that spans your knot. And that number of holes is the genus or crosscap number of the knot.
So it's the best case scenario for that knot's complexity in 3D.
Precisely. The
Yeah.
most efficient surface you can build.
This quantity was first introduced by Clark. and has been computed for torus knots, two-bridge knots, pretzel knots, and others. Further, there exists an algorithm for determining gamma 3D3 for alternating knots and more general algorithms that use normal surface theory.
Okay, so they're just establishing that gamma 3,3 is a well-studied computable thing. It's not new. This is the baseline that they are about to modify.
Now we went to the fourth dimension. Similarly, a compact, smooth, properly embedded surface $5 subset B44F is a subset of B4 with partial F equals K arte. The boundary of F is equal to K is a filling of $2.
And we have to contrast this with the previous definition. Before, the surface $5 was in 3 to 3, our 3D space. Now, the surface $5 is in B4, they're free, which is the four-dimensional ball. The knotted dollars lives on the surface, on the boundary of this ball.
Okay.
So the surface $5 goes into the interior of the 4D ball. It's like, imagine your knot is drawn on the skin of an orange. A spanning surface would be on the skin too. A filling goes through the fruit inside.
That's a great visual. Okay. Let mathcal 4K script F4 of K be the set of all fillings of dollars. The smooth, non-orientable 4 genus of a knot dollar D1FF, and Mikhail of 4K, F and Belma 4 of K equals the minimum of B1 of F, such that F is in script F4 of K.
It's the exact same logic as before. Find the simplest surface, the one with the minimum $1, but this time you're allowed to use the fourth dimension to untangle things.
Which leads to the next statement. Note that gamma 4K, gamma 4 of K is less than or equal to gamma 3 of K.
Yeah, and this inequality is pretty intuitive. Any surface that exists in 3D also exists in 4D. You can just, push its interior slightly into the 4 ball.
And not the other way around.
But not the other way around. In 4D, you have more room to maneuver, so you might find an even simpler surface that you couldn't have built in 3D. Therefore, the 4 genus can be smaller, but it can never be larger.
It's like taking a shortcut through a tunnel instead of having to drive over the mountain.
Perfect analogy.
Okay. They then list some references for gamma 4 and mention Heegard-Floer homology. Then they say this: a non-orientable filling $5 has a second interesting homological invariant beyond its first Betti number, namely the Euler class of its normal bundle, termed the normal Euler number EF into math B, is in 2Z.
A 2Z. That just means it is always an even integer. And this normal Euler number is that twisting quantity we talked about earlier. It essentially measures how much the surface twists around itself in the ambient space. A Möbius strip has a twist. That twist is what's being quantified by this number.
The normal Euler number of a spanning surface is defined to be the normal Euler number of the filling that results from pushing the interior of the spanning surface into $44. Note that the normal Euler number of a spanning surface is the negative of its boundary slope.
That's a critical technical link. In 3D, topologists talk about boundary slope. It measures how the surface meets the knot at the boundary. In 4D, they talk about this normal Euler number.
And they're saying they're the same thing.
They're essentially the same thing, just with a minus sign flipping them. This is what allows them to unify the 3D and 4D theories under one roof.
Okay, here we go. The big moment. We are now ready to define our central object of study, the Euler-normalized non-orientable genus.
Drum roll, please. This is where the magic happens. This is the new tool.
For a spanning surface or filling $5, define its Euler-normalized first Betti numbers to be gamma PMF, sigma capital gamma, plus minus of F equals B1 of F, plus or minus, open parenthesis, sigma of K minus 1/2 E of F, close parenthesis.
Okay, let's freeze frame. We need to look at this equation properly. Gamma P, this is their new invention. It has 3 parts.
Right.
First, you have B$B1 of F. That's the raw complexity, the number of holes.
Okay.
Second, you have sigma K, sigma of K. This is the signature of the knot. It's a well-known number that's a constant for the knot. It doesn't change based on what surface you pick.
And
third is EF, the twisting we just talked about. So they are combining raw complexity, a knot constant, and the surface is twisting all into one number.
And the text explains why they chose this specific combination, where sigma K is the signature of dollars. A key feature of gamma plus F, capital gamma plus of F, capital gamma minus of F, is that it is invariant under the addition of a plus twisted band, as in figure 1.
This is the why. Why this specific weird-looking formula?
It's the noise cancellation thing again.
It is exactly the active noise cancellation analogy. Think about it. When you add a twisted band to a surface, you're introducing noise. It's extra geometric complexity that isn't really part of the knot's essential nature. It's just an artifact of how you built the surface.
So the twist is just static.
It's artificial complexity. And that Euler term in the formula, that minus 1/2 E of F, it generates an anti-wave. It predicts exactly how much noise that twist will create.
Okay.
Well, when you add a twisted band, it changes $B by exactly 1, so the complexity goes up by 1. At the same time, it changes the twisting by exactly plus or minus 2.
Ah, I see.
So the formula calculates -1/2 times 2, which is -1. You get a +1 from the increased complexity and a -1 from the Euler correction.
They cancel out perfectly.
They cancel out.
Hmm.
What's left, the gamma value, is the pure, silent signal of the knot's essential topology, with the construction noise filtered out.
This feature of GEM-half is the origin of the moniker Euler-normalized.
And there it is. They are normalizing by the Euler number to get an invariant quantity.
Next paragraph. As we shall see in section 3.3, a second important feature of the Euler-normalized first Betti number is that it is non-negative, and hence it makes sense to minimize over all spanning surfaces or fillings.
That's a crucial mathematical property. You need a floor. If it could go to negative infinity, you couldn't find a minimum value. The search would never end.
Definition 1.1. The Euler-normalized non-orientable nungia of a not dollar, for $1 and $3 force above, is defined to be MOF men gamma het plus minus n of k equals the minimum of capital gamma plus minus of f, such that f is in script fn of k.
So just like the ordinary genus, we look at all possible surfaces, calculate this new noise-canceled gamma value for each one, and then we pick the smallest one. That's the new genus. The little hat over the gamma hat, gamma usually signifies something that's been normalized or reduced.
They also define an average. We also define the average Euler-normalized newness of dollars to be gammon plus hand colon plus gammon of k equals 1/2 times the sum of gamma hat plus n of k and gamma hat minus n of k.
Right, so they're just creating a symmetric version. Since you can add a positive twist or a negative twist, sometimes it's useful to just average the two to get a central value that isn't biased one way or the other.
Okay, completeness check for subsection 1.1. We've defined the standard genera, gamma 3,3 and gamma 4 dollars. We've defined the normal Euler number. We've introduced the new invariant gamma using the noise cancellation analogy. And we've formally defined the new genera. Have we unpacked all of that?
I think so. That is a solid foundation. The core definitions are on the table. We can proceed.
Subsection 1.2, inspiration from geography questions.
Right, and geography here doesn't mean maps of, France or the Rockies.
Not literal geography.
No, it means mapping the allowable regions of mathematical values. It's a common term in this field.
The definition of the Euler-normalized non-orientable genus arose from explorations into Allen's geography problem for the non-orientable 4 genus. For a not dollar, Allen asked for a description of the set 4k of possible pairs, realized by the normal Euler number and first Betti number, respectively, of a filling of dollars.
Okay, let's visualize this. Imagine a 2D graph. The horizontal axis is the twisting, the Euler number ways. The vertical axis is the complexity, the Betti number.
Okay, I have my map.
Now, every possible surface you can build that fills your knot corresponds to a single dot, a single coordinate on this graph.
Right.
Most of this map is just empty ocean. It's uninhabitable. You mathematically cannot build a surface that would land there. But there's a specific continent, a region of dots, where the math allows surfaces to exist. Allen's geography problem is simply draw the coastline of that island.
We may define 3DI similarly. Note that 3AK subset R4K, R3 of K is a subset of R4 of K.
Again, 3D is a subset of 4D, so the 3D island is smaller and sits somewhere inside the larger 4D island.
As depicted in Figure 2, the set is constrained by the Gordon-Litherland signature bound, with points of Lukami and B sigma E2, sigma K equals the set where B is greater than or equal to 1/2 the absolute value of E minus 2 sigma of K.
Visualizing this wedge is absolutely crucial. It looks like a V shape on our graph. The point of the V is at the coordinate E on the horizontal axis. All possible surfaces, all the dots on our map, must live inside or above this V.
It's a forbidden zone.
Exactly. You cannot have a surface below the V. It's like a deep valley with infinitely steep walls.
In the geography diagram, we may read off gammon K as the lowest height of a point in 1K, whereas hekakana is the minimum vertical distance from anman K to the upward sloping, downward sloping boundary of the sigma.
This is the geometric interpretation of their new quantity. This is brilliant. The ordinary genus, gamma no, is just how low is the lowest dot on the island.
The lowest altitude.
Exactly.
Right.
But the new Euler-normalized genus is how close does the island get to the wall of the V-shaped valley.
Ah, so it's a measure of proximity to the theoretical limit.
That's it, exactly. It's measuring how close the most efficient surface is to the absolute theoretical limit of efficiency.
The geography perspective leads to a reframing of many non-orientable slice torus bounds. That 1.2. For any not dollar, we have maxim plus 4k, but in the maximum of sigma of k minus 2 epsilon of k, and 0 is less than or equal to gamma hat plus 4 of k.
And there's a similar formula for the negative version. Here, this new variable, epsilon of k, comes from a very powerful modern invariant called Heegaard-Flower homology.
So what's the theorem saying?
It's saying that their new geometric distance, the hat gamma value, is bounded below by these deep algebraic invariants. It connects the geometry of the map to the deep algebra of the homology theory.
Okay, completeness check for subsection 1.2. We covered the geography map, the concept of the wedge, sigma, and the geometric interpretation of hat gamma as a distance to the boundary of that wedge. We also stated theorem 1.2. Are we good?
I think so. That's a very clear picture of the motivation. Let's move on.
Subsection 1.3, alternating knots and terrae of genus.
All right, back to 3D space.
Theorem 1.3. A knot dollars is alternating if and only if hat gamma plus 3k, 0 plus 3 of k equals 0 equals gamma hat minus 3 of k.
This is that vanishing property we hinted at earlier. If the knot is alternating, this distance to the V-shaped wall is 0.
So the dots are right on the boundary.
The dots for the best surfaces lie exactly on the boundary lines of the wedge. And this isn't just a property, it's an if and only if. It characterizes alternating knots completely. It confirms that alternating knots are the ground state of this theory.
This theorem shows that the Euler-normalized non-orientable 3 genus can be thought of as a measurement of distance of a knot to the set of alternating knots.
Yeah, it gives us a ruler. If the number is 0, it's alternating. If the number is big, it's very non-alternating. It lets us measure alternatingness.
They then bring in the terrae of genus. Theorem 1.4, for any knot dk gamma 3 of k is less than or equal to g sub t of k.
Now, this is interesting. The abstract said their new quantity bounds the terrae of genus. This theorem statement uses the ordinary non-orientable genus Te. It's a slightly different claim, but it still connects these two worlds.
Corollary 1.5, for k gavelin g t to gavelin g to tk1 and gave hey anyone u sub t to kk1 on good 2k comma 2k minus 1 is greater than or equal to k minus 1.
This just provides a concrete family of torus knots where this terrae of genus gets arbitrarily large, proving the bound is non-trivial.
And then conjecture 1.6, for an adequate knot gamma g sub t of k equals gamma 3 of k.
Adequate knots are a broad class that generalize alternating knots. So they are conjecturing that for this huge important family of knots, the terrae of genus is exactly the same as the non-orientable 3 genus.
That's a bold conjecture.
It's very bold. It would unify two very different looking numbers into one.
Okay, completeness check for 1.3. We've established the alternating knot characterization and the link to terrae of genus, including the conjecture. Let's look at the gaps in 1.4.
Yeah, that's good.
Subsection 1.4, genus gaps. We first addressed the classical question of how large the gap between gamma 3k and gamma 4k can be.
The big question, can the fourth dimension help us infinitely more than the third, or is there a limit to its power?
Proposition 1.7, for any nullity in 1, the Pretzel knot TECOR, Dusovnich R1, P1 and C off die, P equals P of negative K, R negative R minus 1, satisfies. 1 gamma 40P, Bumpy 3P equals 200, 200.
Just look at that difference. The 4 genus, gamma 44, is always 1 for this family, just a simple Möbius strip.
Right.
But the 3 genus, gamma 3, is $2. And since $, can be any integer you want, the gap, 2-1, can be as huge as you want.
So if I'm an ant living on this knot in 3D space, I have to build a surface with, say, 100 holes in it. It's a labyrinth.
A nightmare of complexity, a surface with b to an any.
But if I can just step into the 4th dimension,
Yes,
one step sideways,
the labyrinth collapses. You step sideways, and suddenly the surface smooths out into a simple Möbius strip with just one hole. The 4th dimension effectively deletes the complexity.
is a wormhole.
It is, topologically speaking.
Proposition 1.8. For all odd $1.33, we have hat gamma 33n equals 2 and or gamma hat minus 3 of p of negative 3, 3n equals 2, while hat gamma tat plus 3 equals 0.
This brings us back to the normalized genus. It shows that even when you do the noise cancellation, you can still get non-zero values. It's not always 0.
And finally, the big one. Theorem 1.9. For all $1 in n, there exists a not $, such that 2 and $3kn again, 2 hat minus 3 of kn minus gamma hat minus 4 of kn equals 2n.
And that's the punchline of the whole paper, really. The gap in the Euler-normalized genus can also be arbitrarily large. The wormhole effect is robust. It survives the noise cancellation process.
Subsection 1.5 just outlines the paper structure, so I think we have thoroughly unpacked the entire introduction. Completeness check.
I agree. All paragraphs analyzed, all definitions established at a high level, and the main theorems have been previewed. We are definitely ready to dive into the body of the paper, Section 2.
Section 2, spanning surfaces in 3 dimensions. And it begins with subsection 2.1, boundary slope and 3-dimensional geography.
We touched on this concept, but now we're going to get the rigorous definitions.
The boundary slope of a spanning surface $5 is the rational number, or infinity, corresponding to the isotopy class of the curve partial f on the boundary of a regular neighborhood of $5. For our purposes, it will be sufficient to use the homological definition SF equals LKK equals the linking number of k and k prime.
Okay, that dollars is what's called a push-off. Imagine taking the not dollars and just pushing it a tiny bit away from itself. But along the surface, you get a new curve, k dollars, that follows the original path.
Okay.
The linking number then just counts how many times this new not dollars winds around the old one, $2. That number is the boundary slope.
For a later comparison with fillings and core dimensions, we also define the 3-dimensional normal Euler number of $5 to be 35f E3 of f equals negative s of f.
Just formalizing that connection we discussed.
Okay.
333 is the negative of the linking number.
They then note a modular arithmetic property. In fact, it is well known that the boundary slope of a non-orientable surface is an even integer, and further that E3f equiv, E31f he4e, 3 of f is congruent to s of f is congruent to 2b1 of f modulo 4.
This is like a parity check, or a checksum for the surface. It puts really strong constraints on what combinations of values are even possible. You can't just have any slope in any number of holes. They have to align correctly, modulo 4.
Definition 2.1, geography. The 3-dimensional geography of a not dollars is the subset 3 subset 2 math briefte is a subset of 2z times n of all pairs E3k 1f, where $5 is a spanning surface of dollar.
This is the formal definition of the dots on the map we were talking about earlier. The set of all possible pairs of twist complexity.
They then define the wedge formally again. The addition of a twisted band motivates the definition of a wedge, WEB, centered at a surface with invariants consisting of pairs that satisfy from b 1/2 the absolute value of E minus E is less than or equal to B minus B.
That inequality is the precise algebraic description of that V shape. The slopes of the V are plus or minus 1/2. Any surface $5 generates a whole wedge of other possible surfaces, $2 just by adding twisted bands.
Equation 2.2, big cup F, in math.GT F3, are 3 of k equals the union over f in script F3 of k of W sub f.
And this just says that the full geography, the entire island of possibilities, is just the collection of all these individual V shapes, one for every possible surface. It's the union of all possibilities.
Completeness check for 2.1.
We have the definition of slope, the congruence mod 4, and the union of wedges. I'd say that's clear. On to 2.2.
Subsection 2.2, construction, state surfaces.
Okay, this is a classic, very combinatorial way to build surfaces directly from a 2D drawing of a knot.
First, we define a resolution for a crossing. At each crossing of a diagram dollar of a knot dollars, there are 2 ways to resolve the crossing: a knot-all resolution or a bow resolution, as depicted in Figure 5.
Imagine a crossing. It looks like an X. An A resolution splits it horizontally, so you have 2 little arcs that don't touch. A B resolution splits it vertically.
Okay.
If you go to every single crossing in your knot drawing, and you make one of these 2 choices, you break apart the knot. You end up with a bunch of non-intersecting circles in the plane. It looks like you've completely exploded the knot diagram.
A state surface of a knot diagram dollar is the configuration of disjoint, simple closed curves, called state circles, that results from resolving each crossing of D dollars. To associate a surface to a state, fill each state circle with a disk and attach half-twisted bands at the sites of the former crossings to connect the disks.
This is very visual.
Yeah.
The circles you get become little disks, and the X's where the crossings used to be become twisted ribbons that connect those disks. This process builds a surface that spans the original knot.
Theorem 2.2. For an alternating diagram dollars of knot dollars, the state surfaces generate the geography of dollars. And corollary 2.3, given a diagram dollars, let similar be the set of state surfaces of then 3 cup S, SWFVR3 of K equals the union over F in S of W sub F.
This is a massive simplification, at least for alternating knots. Instead of having to check an infinite number of possible surfaces,
You just have to check a finite number.
right, you only need to check the handful of surfaces that come from these specific states. It turns a deep topology problem into a combinatorics problem. You just count things on a piece of paper.
And they give a formula for that in Lemma 2.4, E3Fs, IDS, BS, ES, WRD, E3 of F sub S equals A of S minus B of S minus the writhe of D.
Yeah, so ESS is the number of A resolutions you chose, ROS is the number of B resolutions, and OBSD is the rise, which is just a count of positive versus negative crossings in the diagram. This allows you to calculate the Euler number, the twisting, just by counting things. No complex geometry required.
Example 2.5 uses the trefoil knot. The all A state gives D3 of F sub S A equals 0. The all B state gives E sub S A FSE E3 of F sub S D equals -6.
Right. The all A state gives what's called the Seifert surface, which is orientable and has no twisting. The all B state gives a highly twisted surface, a Möbius strip with some extra stuff with a twist of -6.
Completeness check on state surfaces.
We've defined the AB resolutions, the construction of state surfaces, the theorem that they generate the geography for alternating knots, and the combinatorial formula for the Euler number. I think we're good.
Subsection 2.3. Construction. Pinch surfaces for torus knots.
Okay, a new family of knots. Torus knots are knots that can be drawn on the surface of a donut without crossing themselves. TPQ means it wraps p times around the long way and 10 times around the short way.
They reference a construction by Batson. Perform a non-orientable band move between two strands of the same component, yielding a new torus knot 2R, ASS. The parameters $true satisfy 1EP2T, SSOQ2R equals the absolute value of P minus 2T.
This is a recursive process. You take a complex torus knot, you pinch two strands together, and it simplifies into a smaller, less complex torus knot. You keep doing this over and over until you're left with the unknot. The surface you build is the trace of all those pinches.
It's like unzipping the knot.
That's a great way to think of it. You're unzipping it step by step back to nothing.
Lemma 2.7 gives the Euler number for the resulting surface. 3,3, F3PQ, ETS3, F3 of P, Q equals -PQ.
A very clean, simple formula. And notice, for the trefoil, which is the T3 and 2 torus knot, the formula gives E -3 pre 2 quite 66.
Which matches the state surface calculation.
It does. It's a nice consistency check. Two different construction methods giving the same answer for the same knot.
Completeness check for pinch surfaces.
Confirmed. It's a recursive construction that unzips torus knots and yields a specific surface with Euler number -P times Q.
Subsection 2.4, essential surfaces.
Right. Now we leave the nice, tidy world of alternating and torus knots and enter the wild. This is for general knots.
They define incompressible and partial incompressible, boundary incompressible surfaces. What does that mean in simple terms?
Incompressible means the surface isn't wasting space. You can't find a loop on the surface that bounds a disk out in the 3D space unless it already bounded a disk on the surface itself. If you could sort of compress the surface along that disk and simplify it.
So essential surfaces can't be simplified.
Exactly. They're topologically minimal. They're the atoms of surface theory for a given knot.
They define something called the rational wedge tilde WV, W tilde of U, and the formula is WV AB, WV, WU tilde V, V. Notice the factor of 2 there. It's slightly different from the integer wedge we saw before. This allows for rational slopes, which you need for essential surfaces.
Proposition $2. For any knot $3, subset tilde of 3 of K is a subset of W tilde of K. This is the entire geography of the knot. All possible surfaces is contained within the collection of wedges generated by just these essential surfaces. So if you can find all the essential surfaces, you've bounded the entire geography. You don't need to look at all the floppy, redundant surfaces.
Lemma 2.11 is labeled the technical core, and it says, let $5 be a surface obtained from $4 by a single partial compression. Then CSF S2 absolute value of S of F prime minus S of F is less than or equal to 2.
This is the engine room of this section.
Yeah.
If you take a surface and you perform a boundary compression, which is a way of simplifying it near the knot itself, the boundary slope can change. But this lemma proves it cannot change by more than 2. It puts a speed limit on how fast the slope can change as you simplify the surface.
The proof looks pretty intense. It involves matrices. Frac U plus 2M plus 1Q, absolute value equals the absolute value of 2 over Q times open parenthesis 2S plus open parenthesis 2N plus 1 close parenthesis Q close parenthesis.
They're using what's called CL2 matrices. These are 2x2 matrices with integer entries and determinant 1. They are the perfect tool for describing transformations on a torus, which is what the boundary of the knot's neighborhood looks like. They show that algebraically, this fraction cannot possibly exceed 2. It's hard algebra doing the work for difficult geometry.
And the payoff is corollary 2.12. Let psi value be any spanning surface for dollars. Then the math UFK is the set of essential spanning surfaces for dollars.
So this is the payoff. Because the slope change is bounded by 2, the gamma value, which depends on the slope, is also controlled. This proves that to find the minimum gamma value, you only need to look at the essential surfaces. You can ignore everything else.
Completeness check for all of Section 2.
I think so. We covered boundary slopes, the constructions for state surfaces and pinch surfaces, and then the crucial bound-on slope change for essential surfaces, which justifies focusing only on them. This sets up the 3D side of the equation perfectly.
All right, on to Section 3, fillings in 4 dimensions.
We are now moving up a dimension, stepping into the wormhole.
Subsection 3.1 is normal Euler number and 4D geography. Lemma 3.1, let $5 be a spanning surface in 3D $3, and let $5 be the filling obtained by pushing the interior of dollars into B4n's, then $4 E3F equals E3F plus E4 of F prime equals E3 of F equals negative S of F.
We mentioned this in the intro, but here it is formally proven. The 4D Euler number of a pushed-in surface is exactly the same as the 3D one. It's consistent.
Then definition 3.2, 4D point crow, the 4D geography, and example 3.3, which contrasts the trefoil with the 52 knot.
Right. So the trefoil, the 3D and 4D geographies are exactly the same. But for the 52 knot, there is a point, the coordinate 2, 1, that's in the 4D geography, but not in the 3D geography.
What does that mean?
It means there's a surface you can build in 4D, specifically a Möbius strip, since $1 that fits into the 4D ball and has a twist of 2. But you cannot build that same surface in 3D space with that specific twist. This is the gap appearing visually on the map.
Subsection 3.2, construction, pinch surfaces, revisited.
They essentially say that the same Batson construction, the unzipping process, works in 4D as well.
Lemma 3.4. The non-orientable filling $50 obtained by applying Batson's algorithm to TPQ has EF2EQ equals R minus PQ.
Notice the difference here. In 3D, back in Lemma 2.7, the formula was just PQD.
Right.
In 4D, it's 2 PQT. There's an extra term, $2. This reflects the extra freedom, the extra wiggle room that the fourth dimension gives you. That $3 is the contribution from the wormhole.
Subsection 3.3, signature and Gordon-Litherland bound.
A classic foundational result in knot theory.
Proposition 3.5. For any filling $5, we have sigma half plus frac 1 of k equals sigma of f plus 1/2 e of f.
This is a beautiful formula that relates the signature of the knot, sigma k, to the signature of the surface itself, and its Euler number. It's a conservation law, in a way.
Theorem 3.6, Gordon-Litherland bound. For any filling dollars, frac B1 absolute value of the fraction sigma of k minus e of f over 2 is less than or equal to B1 of f.
And this is the mathematical inequality that actually defines that wedge sigma we saw in the geography pictures. This theorem proves that the geography must lie inside that V shape. It's the hard and fast rule.
Subsection 3.4, further bounds. Theorem 3.7, Heegard-Flower. Let upsilon denote the Heegard-Flower invariant for any filling 5 epsilon at key f2, absolute value of the fraction 2 upsilon of k minus e of f over 2.
This is a second independent V-shaped wedge. It's centered not on the signature, sigma, but on this other invariant, $2 upsilon.
Corollary 3.8. Theorem absolute value of the fraction upsilon of k minus sigma of k over 2 is less than or equal to gamma 4 of k.
This is a cool geometric argument. If you have two different V-shapes, one centered at sigma and one at $2 upsilon, the geography island has to be inside both of them. The lowest point where they overlap gives a lower bound on the 4 genus.
It's like intersecting two searchlights. The target has to be in the beam of both.
That's a perfect way to visualize it, and that intersection leads directly to the proof of Theorem 1.2, which bounds the normalized genus at gamma.
Completeness check for Section 3?
I think so. We established the 4D definitions. We saw the discrepancy with 3D via the 52 knot example, and we reviewed the two major bounds, Gordon-Litherland and Heegard-Flower, that constrain the geography. This covers the 4D side.
Section 4, Euler-normalized genus agreements.
Right, so now we apply all this machinery to specific important classes of knots.
Subsection 4.1, alternating knots. It starts with 4.1.1, combinatorial proof of Theorem 1.3.
And let's remind ourselves, Theorem 1.3 was the big one. A knot is alternating if and only if its normalized genus cos is 0.
Lemma 4.1, the all-A state surface $5 for a connected diagram dollars has normal Euler number E FA equals 2CR, and first Betty number B dollar FA equals 1 SA plus CRE of FA equals 2 CR minus. B1 of FA equals 1 minus the absolute value of SA plus CR.
These are just formulas that come from counting things on the diagram. Total is the number of crossings, so does the number of circles in the all-A state.
Lemma 4.2. For a connected diagram dollars, we have $2 as des CRE plus SA plus SB.
This is a classic result from applying the Euler characteristic to the sphere that the diagram is drawn on.
Lemma 4.3. The signature of an alternating knot is given by sigma k dash WRD plus SASB.
This is a famous formula by Tratzek. It allows you to calculate the signature of 4D invariant just from the 2D drawing.
The derivation then combines these three lemmas to show that B dollars at frax E1 of FA equals a fraction E of FA over 2 minus sigma of K.
And if you just rearrange that equation algebraically, you get B dollar frax B del dollar. But wait, the definition of gamma plus dollars was B dollars sigma frax. We'll flip, let me reread. Right, the plus version is B dollars plus sigma frax E. So they've proven that gamma plus FB dollars and gamma.
It's a perfect algebraic cancellation.
It is. The math just clicks into place beautifully. It proves gamma is 0 for alternating knots just from counting.
Then, 4.1.2 topological proof, Green's characterization. A knot is alternating if and only if it bounds both a positive definite and a negative definite spanning surface.
The definite surface is one where its signature is as large as possible for its complexity. If you plug that property into the Gordon-Litherland bound, you immediately find that the surface must lie on the boundary of the wedge, which means the distance is 0. So this confirms the same result using deep topology instead of simple combinatorics.
Subsection 4.2. Relation to Tureyev genus.
The Tureyev surface is built by essentially starting with the all A state circles and then adding saddles to transition to the all B state circles.
Formula 4.2, Frike 12 plus CRS SSB, del sub T of D equals 1/2 times open parenthesis 2 plus CR minus magnitude SA minus magnitude S of D close parenthesis.
And the proof in the paper shows that this Tureyev genus is exactly the average of the gamma values for the A and B state surfaces. It's a direct connection.
Subsection 4.3, torus knots. They do a deep dive on one example, proposition 4.5, analysis of T4 3 point.
Right, and this is an important counterexample of sorts. They show a few things. First, gamma 3, gamma 4 chord. The 3D genus is 2, while the 4D genus is 1.
So there's a gap.
There's an ordinary gap.
Oh.
But second, they show that hey gamma plus 3 equals base to a Euler. The normalized 3 genus is 0. This shows that even if the ordinary genus is large, the normalized genus can be 0. The knot is close to alternating in this new normalized sense, even if it's complex in the ordinary sense.
Okay, that covers it. Completeness check for section 4.
We proved the alternating knot theorem 2 different ways. We linked it directly to the Tureyev genus, and we analyzed the interesting case of the T4 $3 knot. I think we're solid.
Section 5. Ordinary genus gaps. Pretzel knots.
Now we get to the business of generating those huge arbitrary gaps.
Proof of proposition 1.7, the knot is that pretzel knot PP equals PK ordinary R1 dots.
Right. And they use a sequence of what they call type I and type 2 band moves. A type I move is a special kind of change that preserves the knot type up to something called concordance. A type 2 move is one that simplifies the knot until it becomes the unknot. By chaining these moves together in the fourth dimension, they show that this complicated pretzel knot is concordant to something that bounds a simple Möbius band, which has d(11 $1). So the 4 genus must be 1.
Yeah, but what about the 3 genus?
They cite a result by Ichihara and Mizushima. In 3D, you can't do those clever band moves. You're stuck. And the genus stays high at $2, hence the gap. $2 versus 1, 1.
Proposition 5.1. The gap between normalized genera is at most 2 for these knots.
This is the surprising part. Even though the ordinary gap is huge, the normalized gap is tiny. This suggests their gamma invariant is capturing a more stable kind of complexity, one that doesn't fluctuate so wildly between 3D and 4D for this particular family of knots.
Completeness check for section 5.
We established the infinite gap for the ordinary genus and the small bounded gap for the normalized genus on these pretzel knots. That's clear.
Section 6. Euler-normalized genus gaps.
This is the heavy lifting of the paper. This is where they have to find a family of knots, where the gap in the normalized genus is the one that gets big.
The target is the family of knots Pount 3, 3, and int for odd longest 3 3s.
Right. And it's known that this knot is what's called slice, which is a very strong condition. For our purposes, it means that its normalized 4 genus, hot gamma 4, is 0.
So the goal is to show that the 3 genus, hot gamma 3, is not 0.
Exactly. They want to show it's 2.
To do this, they use a tool called Hatcher-Ortel edgepath systems. We really need to slow down here. This is by far the most technical part of the paper.
I agree. The Hatcher-Ortel algorithm is an amazing but complicated machine. It's a way to find all the essential surfaces in the space around a pretzel knot. It turns a very difficult topology problem into a pathfinding problem on a graph.
Decompose 3 $3 into 2 P3 3 3 3s. Stop. Decompose 3D 3 3 into balls. That sounds like we're chopping up the universe. What are we actually looking at?
Imagine the empty space around the pretzel knot. We aren't just looking at it as one big void. We're slicing it up into manageable geometric chunks, specifically these balls with tangles inside, like building blocks.
Like Lego bricks for 3D space.
Exactly. And the edge path isn't a path in physical space. It's a path through the possibilities of how a surface can cut through these blocks. We are navigating a map of potential surfaces.
The edge path diagram. The vertices of MathCan are the rational numbers, and we use coordinates, Langle PQ, 10 in Q, angle bracket P over Q equals.
They're just mapping the rational numbers, which represent the boundary slopes, onto a 2D coordinate system to make it easier to draw.
Basic edge path, sigma P and perpa pin.
These Greek letters represent specific configurations of the surface inside the tangled parts of the pretzel knot. They are the fundamental building blocks of the paths.
Edge path systems for 2n. They list 8 basic systems, lambda K2 through lambda 1 and nil.
These are the allowed combinations of the basic paths for the 3 tangles of the pretzel knot, 23 3 topologicals. You have to pick one path for each tangle, and they have to match up correctly at the boundaries.
They then define 3 types of extensions, type I, type 2, and type 3.
These are just the rules for how you can glue the surfaces together across the different regions of space.
They then isolate a very specific type I system called lambda, and they list the fractions involved, Langle 12 wrangle, Langle 0 wrangle, and Langle 1 in hell, Langle doll, Langle 13 wrangle, and Langle 1 hell wrangle.
This type I system is the most complex and interesting one. It's a prime candidate for the surface that might minimize the genus, so they have to analyze it very carefully.
Subsection 6.2, computations on edge path systems.
Now they have to actually calculate the Betti number and the Euler number for these paths they've constructed.
They define a twist tau of E equals -2 epsilon of E times magnitude E.
This is a clever formula that converts the geometry of the path on their diagram, its length and direction, into the topological twist of the surface it represents.
Then, computation for type I surface. This gets very specific. The result is $b samda francus 3 1 of lambda I equals n plus 3 over 2, and the normal Euler, frax m plus $1 equals -8 over n plus 1.
Look at those formulas. They depend on no $1 as null gets bigger. The complexity, $r grows, and the twisting goes to 0.
They plug this into their master formula. Gamma frac 4 n plus 1. Capital gamma minus of lambda I equals n plus 2 over 2 minus 4 over n plus 1.
And the important thing is that for $1 3D3n's, this value is roughly 222. It is definitely not 0. In fact, it gets bigger as null gets bigger.
Proof of proposition 1.8 conclusion. They say one may check that the minimal value of gamma among type 2 and type 3 surfaces is 2.
Right. They checked all the other simpler paths, which they summarize in Table 1, and the lowest value they could find was 2. Since the type I value we just saw is much higher, the minimum overall must be 2.
So hat gamma dash 3pn is port 2.
And we already knew the hat gamma 4pn equals an odd slice. The gap is $2 equals 2002. They found it.
Completeness check for the beast, that was section 6.
That was dense. But we covered the Hatcher-Ortel framework, the edge path diagram, the specific computation for the lambda surface, and the comparison with the other types to prove that the minimum value is 2. We found the gap. I think we're clear.
Section 7, Euler-normalized genus gaps, connected sums.
The final step, they have a gap of 2. Can they make it bigger?
Lemma 7.1, let $k and $k be knots in 3F30, then hat trick pass ho PM3 plus Bama hat plus minus 3 of K0 connected sum K1 equals.
This is additivity. The connected sum, $k, and 1, is what you get when you cut open both knots and splice them together. This lemma says the normalized genus of the combined knot is just the sum of the individual genera. This is non-trivial to prove, because sometimes surfaces can interact in weird ways, but the proof shows that their gamma invariant behaves very nicely.
And now, Theorem 1.9, the grand finale. Construct a $0 in the home, key 333, the connected sum of n copies of P of -333.
So they take that specific pretzel knot we just analyzed, the one with a normalized gap of 2, and they just tie null of them together in a big chain.
Okay.
The normalized 4 genus is still 0, because $0 plus dots plus dollar is still 0.
Right.
But the normalized 3 genus becomes $2 plus 2 plus dots plus 2, which is $2.
So the gap is $2.
The gap is $2. Conclusion. The gap can be arbitrarily large.
And there we have it. The unabridged protocol is complete. We've reached the end of the paper.
We have.
Completeness check for section 7.
The additivity lemma plus the connected sum construction proves the arbitrary gap. Confirmed.
We've made it to the outro.
We did.
That was intense. But I feel like I actually understand this paper now, which is not something I can usually say.
Me too. It was a journey. But think about the path we just traced. We started with a very clever definition that normalized complexity against twisting our noise cancellation. We saw it categorize alternating knots perfectly. We saw it connect to the Thea of genus. And finally, we saw that even with this careful normalization, the fourth dimension still offers an arbitrarily large wormhole compared to the third dimension.
So here's the provocative thought I want to leave everyone with. The paper establishes that HACK-gamma 3 measures the distance to being an alternating knot, and HACK-a 3 measures the distance to being a slice knot. So the gap, the difference between them, HACK-up 4, represents something very specific. It represents the complexity of a knot that can only be resolved by the fourth dimension.
A purely four-dimensional complexity.
Exactly. A complexity that is completely invisible to the third dimension, but is captured by this gap. So the question is there a physical meaning to this? If these knots were, say, tangled DNA strands or cosmic strings or magnetic flux tubes, what would this 4D gap represent in reality? Is it some kind of potential energy? Is it a measure of stability? What does it mean?
That is a question for the next deep dive.
Thank you for listening to this special edition. Bye-bye!
Welcome back to the deep dive. Today, we're doing something fundamentally different.
We are.
Usually, we take a pretty broad look at a topic, sort of skimming the surface to find the shiny object.
Right, the big picture.
But today, we're going deep. We're embarking on a very specific, very rigorous journey right into the architecture of low-dimensional topology.
It's a pleasure to be here. And you're absolutely right. Rigorous is the word of the day. We are looking at a single paper.
Just one.
It's titled On the Non-Orientable 3 and 4 Genera of a Knot, Connections and Comparisons, and it's authored by Knihs, Patel, Rugg, and Sabloff. The release date on the preprint is February 16th, 2026.
And this paper is, well, it's dense. It is filled with inequalities, theorems, very specific geometric constructions. So before we even jump in, I think I need to establish the rules of engagement for this session.
Okay.
We're going to be operating under what we're calling the unabridged protocol.
The unabridged protocol. That sounds intense. What does that actually mean for us and for you listening?
It means we are going linearly through this material. We are not skipping the dense parts. We're not summarizing over the hard math to spare anyone's feelings.
No shortcuts.
None. We are going to deconstruct this paper sentence by sentence, formula by formula. If there's a theorem, we read the theorem. If there's a Greek letter, we pronounce it.
I mean, it's really the only way to truly understand the structure of the arguments they're building here. We have to be thorough.
Exactly. So our mission is to understand a new quantity introduced in this paper, something they call the Euler-normalized non-orientable genus.
Right. And we're going to see how it relates to knots, the surfaces that span them, and this idea of the geography, which is a term we will definitely define, of those surfaces in both three-dimensional and four-dimensional space.
We'll explore how this new genus can bound another one, the Thea of genus, and how it connects to a special class of knots called alternating knots.
And maybe most excitingly, how it reveals these fundamental gaps, these huge differences between dimensions when we look at a family called pretzel knots.
All right. That covers our mission statement and the protocol. Does that set the stage sufficiently?
The parameters are crystal clear. We are ready to begin the analysis.
Excellent. Let's move to section 1, introduction. We're going to start right at the top with the abstract. The authors state, we define a new quantity, the Euler-normalized non-orientable genus, to connect a variety of ideas in the theory of non-orientable surfaces bounded by knots.
Okay, right off the bat, Euler-normalized is the key phrase we need to lock onto. In topology, the genus is, basically a measure of complexity. Think of it like how many holes or handles a surface has.
And non-orientable.
That means we're dealing with surfaces like Möbius bands, which only have one side. You can't paint the front red and the back blue because, well, they connect. There is no front and back.
So Euler-normalized must be some kind of adjustment to that genus.
Precisely. It implies they are adjusting this complexity measure based on something called the Euler characteristic, or more specifically, the normal Euler number, which has to do with how the surface twists in space.
Okay. The abstract continues. This quantity is used to reframe non-orientable slice torus bounds on the non-orientable 4 genus. Let's unpack slice torus bound.
Right. So a slice knot is a knot in our 3D space that can be, let's say, filled in with a smooth disk in 4D space. Think of our 3D world as just one slice of a 4D reality. If your knot can be the boundary of a simple disk in that higher dimension, it's called slice.
And the slice torus bound.
And that usually refers to these powerful inequalities, often coming from a field called Heegaard-Floer homology, that put limits on the complexity of that filling surface in 4D. So when they say they're reframing this, it means they're going to take these known powerful inequalities and translate them into this new language of Euler normalization.
Got it. Next, they say they use this new quantity to bound below the Thea of genus as a measure of distance to an alternating knot.
The Thea of genus is a really fascinating invariant. If you have a knot diagram, a drawing of the knot, the Thea of genus tells you, loosely speaking, how far that drawing is from being alternated.
And alternating is?
It's where the crossings go over, under in a perfect pattern. If the Thea of genus is 0, the knot is alternating. If it's higher, it's more complex, more jumbled. So they are claiming their new genus provides a new floor, a lower bound, for this complexity measure.
And finally, they mentioned understanding gaps between the 3- and 4-dimensional non-orientable genera of pretzel knots. And they also connect this to essential surfaces and the slope conjecture.
Right. Pretzel knots are just a specific family of knots built by twisting strands together in columns. They look, well, like pretzels. They are fantastic testing grounds for these theories because you can control their properties very precisely.
Well, the gap.
The gap refers to the difference in complexity when you look at the knot in 3D versus what you can do with it in 4D. And the slope conjecture is a really deep and still open question that tries to connect quantum invariants like the Jones polynomial to the geometry of these surfaces.
Okay, I think that covers the abstract. We've defined the scope of the paper. Have we missed any nuances in this initial summary?
I think we've unpacked the terminology sufficiently for an abstract. The key terms are on the table. We can define them more formally as they appear in the text. Let's proceed to section 1.1.
Perfect. Moving to section 1.1, non-orientable genera of a knot. The authors begin by setting up their notation. They write, to define the Euler-normalized non-orientable genera of a knot-collar subset S33, we begin by setting notation.
Okay, so R is our knot. The expression is not a collar subset. S33K is a subset of S3. Here, 3S33 is the 3-sphere. The easiest way to think about it is just as our standard 3-dimensional space, but with a single point added at infinity to close it up, the same way a circle is just a line with a point at infinity connecting the ends. It's the standard playground for knot theory.
Then they define a spanning surface. They say a compact, smooth, embedded surface, right-Euler subset S33 with partial f is the spanning surface, is a spanning surface of dollars.
So partial f, the boundary of S, is the mathematical notation for the boundary or the edge of the surface, 5 Eulers. This sentence just means the knot dollars is the edge of the surface dot.
Like a soap film in a wire loop.
Exactly. The wire is the knot, $. The soap film is the spanning surface, $5. But since we're talking about non-orientable surfaces, that soap film might have a Möbius-style twist in it.
They denote mathcal 3K as the set of all such spanning surfaces in 3D. Then they get to the first big definition, the non-orientable 3 genus, which is also called the cross-cap number. Here's the formula.
Okay.
The expression for the 3 genus is gamma 3K mundi B1F.
That's gamma 3 of K equals the minimum of B1 of F such that F is in script F3 of K.
So what is B the Leskill?
Let's break that down. VBLRS B1 of F is the first Betty number. For a connected surface that has a boundary, like our soap film, this number just counts the number of holes or non-separating loops in the surface itself. A simple disk has B$1 equal to 0. A Möbius band has B$ equal to 1.
So the genus gamma 3K is asking, what's the simplest possible non-orientable surface you can find that has this knot as its boundary?
Exactly. We minimize the Betty number to find that simplest version. It's the least complex surface that does the job.
The paper notes this was introduced by Clark and has been computed for various knots. Then they move to the 4th dimension. Similarly, a compact, smooth, properly embedded surface $4 subset B4 with partial F prefactor is a filling of dollars.
Right, so now we're in $4 B4, which is the 4-dimensional ball. The boundary, or the skin, of the 4 ball is the 3-sphere, 3s3 So our knot dollar lives on the skin of this 4D ball, and the surface $4 dips down into the interior. This is called a filling.
It's very hard to visualize.
It is. A common analogy is to imagine the knot just floating in our 3D space, and the surface hangs down from it into a 4th dimension, maybe time like a curtain or a sheet.
Okay, so with that setup, they define the non-orientable 4 genus with this formula. gamma 4k in math 4k.
Phonetically, that's gamma 4 of k equals the minimum of b1 of f, such that f is in script f4 of k.
So it's the same minimization problem.
It is, but the set of allowed surfaces, which is mathcal 4k script f4 of k, is much, much larger because we have this whole extra dimension to move around in.
And the paper immediately note that gamma 3k.
That would be gamma 4 of k is less than or equal to gamma 3 of k, and this is absolutely crucial.
Why is that?
Well, because any surface you can build in 3 dimensions can just be pushed a tiny bit into the 4th dimension. So any surface in the 3D set is also in the 4D set. But in 4D, you might be able to resolve intersections or untie things in a way that's totally impossible in 3D.
Right, like how you can untie a knot drawn on paper by lifting it up into 3D.
That's the perfect analogy. So the minimum complexity in 4D, the 4 genus, can be smaller. It's often easier to span a knot in 4D.
Okay, now they introduce the next key ingredient, the normal Euler number. They say a non-orientable felling $5 has a second invariant, the Euler class of its normal bundle, which they call the normal Euler number, in the 2 math BBZ.
And that's E of F is in 2Z.
So it's an even integer.
Yes, $2 math BBZ totally just means the set of even integers. The normal Euler number measures how much the space around the surface twists. If you were walking along the surface, it's a measure of how the up direction twists as you go. For non-orientable surfaces, this is a bit subtle, but it essentially captures a kind of self-intersection number if you were to perturb the surface slightly. It's a measure of twistiness.
And here we go. This is the core definition of the paper. They are ready to define the Euler-normalized first Betti numbers. The formula is B1FF.
Phonetically, that's capital gamma plus minus of f equals b1 of f plus or minus the quantity, sigma of k minus 1/2 e of f. This is the star of the show.
So let's look at the components. We have $f, which is the complexity. We have EFers, the twisting. What's sigma?
Okay. Sigma of k is the signature of the knot. It's a classical, very famous knot invariant that you can calculate from something called a Seifert matrix. For our purposes, it's a fixed number associated with the knot dollars.
So why combine them in this very specific way?
The authors explain it using what they call twisted bands, and they reference their figure 1.
Right. They say that adding a twisted band to a surface changes $b by +1 and changes by PM22.
Let's picture that. Imagine you have your surface. You take a little strap, a little band, and you attach it to the surface, but you put a half twist in the strap before you glue it down. You've just added a handle, so the Betti number, $1, goes up by 1.
Okay, that makes sense.
But that twist in the band also changes the normal Euler number. Depending on whether you twisted it left-handed or right-handed, the Euler number daler changes by either +2 or -2.
Ah, and now I see it. If you look at the formula for gamma plus dollar.
Or gamma plus capital gamma plus, yeah.
The term is -1/2 e. So if dollar changes by +2, that term changes by -1.
Which perfectly cancels out the +1 change from the Betti number.
So gamma plus dollar stays constant.
Yeah.
It's invariant when you add a positive twisted band.
Yeah. And similarly, gamma capital gamma minus is invariant when you add a negative twisted band. This creates a new quantity that is stable. It doesn't care about these specific geometric operations. It filters out the noise of just adding superficial twists.
That's very elegant. So definition 1.1 formalizes the genus itself. It says min gamma f in math in k.
And that's gamma hat plus minus n of k equals the minimum of capital gamma plus minus of f, such that f is in script fn of k.
So just like the ordinary genus minimized the Betti number.
This new Euler-normalized genus minimizes this new stable quantity, gamma t, and they define it for both 1 NDLE3 surfaces in 3D and 1 NO4 Forto fillings in 4D. It represents the core complexity of the knot that you can't get rid of just by adding some simple twists.
Wow, okay. That brings us to the end of section 1.1. That was a lot of definitions. Have we fully established the vocabulary required to proceed?
I think so. We've defined the ordinary genera, the normal Euler number, and this new Euler-normalized genus for both 3 and 4 dimensions. And most importantly, we established why it's invariant under twisting. I believe we have thoroughly unpacked it. Let's proceed to the geography in section 1.2.
All right, section 1.2. Inspiration from geography questions. The authors mentioned something called Allen's geography problem. What exactly is the geography of a knot?
It's a visual metaphor and a really useful one. For any given knot, every valid surface that spans it has a pair of numbers. EB, JOAE, comma B, that's the normal Euler number, and the first Betty number.
Right.
If you plot these pairs on a 2D grid with dollars on the x-axis and $s on the y-axis, you get a kind of map, a scatter plot of all possible surfaces. And Alan asked, what regions of this map are populated? Where can surfaces actually live? That's the geography.
And the paper states that this geography is constrained by something called the Gordon-Litherland signature bound. They describe a wedge in this grid.
Yes. The expression for the wedge is F1p sigma.
That's W sigma equals the set where B is greater than or equal to 1/2 the absolute value of E minus 2 sigma of K.
So let's visualize that. It's a V shape, a wedge on our graph. The pointy bottom of the wedge, the vertex, is at the point E equals 2 sigma. E equals 2 sigma of K on the horizontal axis.
And the sides go up from there.
Exactly. The sides slope up at what is essentially a 45-degree angle. This inequality says that all the points in our geography, all the valid surfaces, must live inside or above this V shape. You can't have a surface with a very low Betty number, Baller, if its Euler number is very far away from the signature value.
Then they say something really insightful. The Euler-normalized genus is the minimum vertical distance from the geography to the boundary of this wedge.
That is a beautiful geometric interpretation. It's perfect. The ordinary genus is just asking how low can you go on the b-axis, just the absolute minimum value of $.
But this is different.
This new Euler-normalized genus is asking how close can you get to the theoretical limit? How close can you get to the edge of that wedge? If a point, a surface, lies exactly on the boundary of the wedge, its Euler-normalized genus is 0. It means that surface is as efficient as it could possibly be relative to its own twisting.
And they use this to preview Theorem 1.2, which reframes a bound from Heegaard-Floer theory. The inequality is 1 na little take cam plus 4k.
Phonetically, the maximum of sigma of k minus 2 epsilon of k comma 0 is less than or equal to gamma hat plus 4 of k.
So what's the new letter, epsilon k?
Epsilon of k is the epsilon invariant. It's a very powerful tool from this modern theory called Heegaard-Floer homology. What this theorem does is connect their geography perspective to these really high-powered modern invariants. It basically says the gap or the difference between the signature wedge and another similar wedge defined by epsilon can force the Euler-normalized genus to be non-zero. You have two different constraints pushing the complexity up.
Okay, that covers the geography and the visual intuition behind this new genus. Does that cover every nuance of section 1.2?
I think so. We've visualized the wedge, we've defined the geometric meaning of the new genus, and we've seen how it connects to other known invariants. We are ready to move to the roadmap.
All right, section 1.4, roadmap. This section in our discussion is covering sections 1.3 through 1.5 in the source text. They list several key theorems. Theorem 1.3 states, a knot is alternating if and only if gamma PM3k equals 0.
And that's gamma hat plus minus 3 of k equals 0.
This seems like a very strong statement.
Oh, it's a huge classification result. It says this new genus is a perfect detector for alternating knots. If the normalized genus is 0, the knot must be alternating. And if the knot is alternating, the genus must be 0. It's an if and only if statement, which is the gold standard in math.
Then Theorem 1.4 relates their genus to the Tareyev genus, Duji Tide A. And they also foreshadow the gaps section, noting that the 3 genus and 4 genus can be very different.
Right, and this really sets up the central conflict of the paper. We have these 3D properties and these 4D properties. As we said, 4D is supposed to be simpler. They want to quantify exactly how much simpler it can be. The gap is the measurement of that difference.
Okay, that concludes the introduction. We've defined our terms, we've visualized the geography, and we've previewed the main results of the paper. Are we ready to dive into section 2? Spanning surfaces in 3 dimensions.
We have a clear map of where we are going. Let's begin the technical work in section 2.
Section 2.1, boundary slope in geography. We're returning to this idea of the boundary slope. The formula they give is ZS F LK KK.
That's S of F equals a linking number of K and K prime.
So what is Dollar?
KK prime is what's called a push-off of the knot. Imagine you take your knot dollars and you just nudge it slightly along the surface, $5, just a millimeter away from its original position. Now you have 2 knots, the original and this new ghost copy.
And you count how many times they link.
Exactly. You count how many times this new knot polar links through the original dollars, that's the linking number, irlo k. And crucially, the authors note that for surfaces in 3D, the normal Euler number is just the negative of this value. So E3FF E3 of F equals negative S of F.
They also introduce some modular arithmetic. The relation is E3F limit italic F equif 2B1 F fill 4.
That's E3 of f is congruent to S of f, which is congruent to 2b1 of f modulo 4.
What's the point of this?
This is a parity constraint. It tells us that you can't just have any pair of integers show up in your geography. They have to match up in a specific way, modulo 4. It creates a kind of checkerboard pattern on our geography grid. You can only land on the black squares, not the white ones.
Okay, that makes sense. They then formally define 3a few k, R3 of k, as the set of all these realizable pairs on the grid. Does that cover section 2.1?
Yes, we've defined the slope, its relationship to the Euler number, and the modulo 4 constraint. We're good to proceed to state surfaces.
Section 2.2, state surfaces. This sounds like a constructive method. They describe using a knot diagram. You have crossings, and you can smooth them in two ways, what they call A resolution and B resolution.
Right. Imagine a crossing that looks like an X. An A resolution is where you smooth it vertically. You join the top left strand to the bottom left and the top right to the bottom right. A B resolution is smoothing it horizontally, joining top left to top right.
And if you do this for every single crossing in the diagram,
the knot completely falls apart into a collection of simple, non-intersecting circles in the plane. These are called the state circles.
And how do you turn those circles into a surface?
Well, you fill in all the circles with flat disks, and then where the original crossings were, you put in little twisted bands to reconnect all the disks into one single surface.
They cite a result, Theorem 2.2 by Adams and Kindred, which says that for alternating knots, these basic state surfaces generate the geography.
This is an incredibly powerful computational tool. It means we don't have to go hunting for mysterious surfaces out in the void. We can just look at a diagram of the knot, generate all the surfaces that come from choosing A or B at each crossing, and those surfaces, plus the twisted bands we can add, will cover the entire geography grid. It reduces a deep topological problem to a combinatorial one.
And they provide a formula for the Euler number of these state surfaces in Lemma 2.4. The formula is 3/3fs. AS, BS, WRD.
Phonetically, that's E3 of Fs equals A of S minus B of S minus the writhe of D. Let's parse that.
Go ahead.
Phi of S dollars is the surface that comes from a specific state, a specific set of choices. It S is the number of A resolutions you chose, ES is the number of B resolutions, and 2 right of D is the writhe of the original diagram, which is just the sum of the signs of all the crossings. This reduces the calculation of that geometric twistiness number to just simple counting from the diagram.
And they apply this to the trefoil knot in example 2.5. They look at two basic surfaces, the classic Seifert surface and a Möbius band.
Right. The Seifert surface comes from choosing all A resolutions, and they calculate its parameters as $2 and B is 22. For the Möbius surface, which comes from another choice, they find $3 on 6/6 and bud dollar equals 11.
And those 2 points are enough.
For the trefoil, yes. If you plot the point $2 and the point $6 on the grid, and then you draw the wedges of surfaces you get by adding twisted bands, you reproduce the entire known geography of the trefoil. It verifies the theory beautifully.
They do something similar for the 52 knot in example 2.6, finding 3 basic surfaces are needed there. Okay, does that cover the construction and calculation of state surfaces in section 2.2?
I believe so. We've explained the resolution algorithm, the construction of the surface from circles and bands, the formula for the Euler number, and we've seen it work with the trefoil example. We have thoroughly unpacked it. Let's move to pinch surfaces.
Section 2.3, pinch surfaces. This seems very specific. It's about torus knots, which are knots of type TP TQ dollars. They describe something called a pinch move.
Right. A torus knot is a knot that can be drawn on the surface of a donut without crossing itself. A pinch is a move where you take 2 parallel strands of the knot on that donut surface and you sort of pinch them together by adding a band between them. It's a surgical operation that simplifies the knot.
And they use this to define new surfaces. They have some parameters. True lore is the expressions are tor equals p to any n and zors equals q to any inch.
Phonetically, R equals the absolute value of p minus 2t. S equals the absolute value of Q minus 2H. These look like some kind of number theoretic reductions based on the original winding numbers, 2 and $8, and how many pinches you've done.
The payoff is Lemma 2.7, which gives the Euler number for these surfaces. The formula is E3 F3 PQ equals negative PQ to or.
Which is E3 of F3 of PQ equals negative P times Q. A very clean and simple result.
It is.
It says that for any torus knot T mano Q, we can construct a very specific non-orientable surface, this pinch surface, and its Euler number is just negative the product of P up or dollars. This gives us a concrete, calculable data point on the geography grid for this entire family of knots.
Is that sufficient for section 2.3?
Yes. The pinch surface gives us a specific, calculable data point for torus knots. Let's discuss essential surfaces next.
Section 2.4. essential surfaces. Now, the authors dive into some really core three-manifold topology terms, compressing disks and boundary compressing disks.
Right, this is the rigorous stuff. A surface is compressible if there's a kind of superfluous handle that you can get rid of. Imagine a loop on your surface that bounds a disk, but the disk isn't part of the surface. If you can use that disk to perform surgery and simplify the surface, it was compressible.
And a boundary compressing disk is similar.
Very similar, but the disk in question also touches the boundary of the space around the knot. A surface is called essential if you can't do either of these compressions. It's fully simplified, it has no fat left to trim.
Okay, so these are the most efficient surfaces. They then define something called a rational wedge. The definition is the aptXD key tilde being Q for its math ABN.
That's W tilde of UV equals a set of pairs EB in Q cross N such that the absolute value of E minus U is less than or equal to 2 times the quantity B minus V.
It looks just like the wedge from before.
It is the same V shape, but it's been generalized. The center of the wedge is now allowed to be a rational number, not just an integer. This is because these essential surfaces can have fractional boundary slopes.
And the big takeaway is proposition 2.10. It states, the geography $3K is contained in the union of wedges of essential surfaces.
This is the key structural result of this section. It says if you want to understand the entire geography of not all the infinite possibilities, you don't need to look at every surface. You only need to find the finite number of essential surfaces. Their wedges cover everything else.
It reduces an infinite problem to a finite one.
Exactly. And the final piece is lemma 2.11, which bounds the slope change. They say the boundary slope change is bounded by 2.
So when you do one of these compressions, the slope doesn't jump around wildly.
Right, it's controlled. And that control is what allows them to prove that all the other non-essential surfaces stay neatly inside the wedges defined by the essential ones.
That finishes section 2. Does that cover every nuance of spanning surfaces in 3 dimensions?
I think it does. We've covered state surfaces for alternating knots, pinch surfaces for torus knots, and the general theory of essential surfaces that bounds the entire geography. We are ready to move to the 4th dimension.
Section 3. Fillings in 4 dimensions. We start with section 3.1, normal Euler number and 4D geography. They define a cobordism in the space at 1 times S33.
Right. A cobordism is a surface that connects one thing to another through a higher dimension. In this case, it connects R naught sitting at time $2 to, well, nothing, the empty set, at time $2. It's a surface that fills in the knot through this time-like dimension.
They give a formula for the 4D Euler number using something called the blackboard framing. The formula is E vars F, WRDR D01.
Which is E4 of F equals the writhe of D0 minus the writhe of D1.
So you can calculate it just from diagrams.
Yes. If you think of this cobordism as a movie of knot diagrams evolving over time, you can calculate the 4D Euler number just by looking at the writhe of the diagram at the start of the movie, D dollars, and the writhe at the end, D dollars. It's a very practical way to compute these 4D invariants.
Now, lemma 3.1 seems crucial. It says the 3D and 4D Euler numbers match for spanning surfaces.
This is a really important consistency check. It confirms our definitions make sense. If you take a surface that lives in 3D and you just push it a little bit into 4D without actually changing its topology, its Euler number doesn't change. The 3D world is a consistent subset of the 4D world.
But things can be different. They bring up the 52 knot again in example 3.3. They say the 52 knot has a filling in 4D, Euler number 2, Betty 1, that doesn't exist in 3D.
This is the first hard evidence of the gap we talked about. In the 4D geography, there is a valid surface at the point $2 on our grid, but in the 3D geography, that point is empty. You can do something in 4D specifically, a kind of move called a flat band move, that you simply cannot do in 3D. The 4th dimension provides a shortcut.
Okay, does that cover section 3.1?
Yes, the definitions and the clear discrepancy shown by the 52 knot are laid out. Let's revisit pinch surfaces in 4D.
Section 3.2, pinch surfaces, revisited. They're back to constructing surfaces for torus knots, but now in the 4-ball. Lemma 3.4 gives the Euler number. The formula is E FPQ equals R PQ2.
And phonetically, that's E of F of PQ equals R minus PQ.
So how does this compare to the 3D case?
Well, remember, the 3D formula was just SUA 3PQ. Here we have this extra term, $3. This $3 comes from the specific way the pinching process works in 4D. It shows, right there in the formula, that the geometric properties of the surface have shifted. The geometry is different in 4D.
That covers 3.2. Let's move to section 3.3, signature and Gordon-Litherland. They introduce the Gordon-Litherland symmetric bilinear pairing.
This is a way of defining a kind of inner product on the loops within the surface. It lets you measure orthogonality on the homology of the surface, and from that pairing, you can define a signature for the surface itself. It's where linear algebra meets topology.
And proposition 3.5 relates the knot signature to the surface signature. The formula is
Sigma k,
sigma f plus frac 1 2 f.
or sigma of k equals sigma of f plus 1/2 e of f. This equation is like a conservation law. It ties the knot invariant sigma, which is fixed for a given knot, to the invariance of the surface sigma and e of fn.
And this all leads to theorem 3.6, the famous Gordon-Liberland inequality. The inequality is fractio b1.
Which is the absolute value of the fraction. Sigma of k minus e of f over 2 is less than or equal to b1 of f. This inequality is the mathematical definition of that wedge, W sigma, we talked about at the very beginning. This proves that all surfaces must lie inside that V shape. It also proves that the Euler-normalized genus is always non-negative. You can't cheat the signature.
Does that cover section 3.3?
We have established the lower bound derived from the signature. Now we need the other bound from Heegard-Floer homology.
Section 3.4, further bounds. They cite theorem 3.7, the upsilon bound. The inequality is frac2 b1 f2.
That's the absolute value of the fraction. 2 upsilon of k minus e of f over 2 is less than or equal to b1 of f.
So it's another wedge.
It's exactly another wedge. Just like the signature sigma creates a wedge centered at $2 sigma, this upsilon invariant upsilon creates another wedge, this one centered at $4 upsilon. So now we have 2 of these V-shapes on our geography grid.
And any real surface has to lie inside both of them?
It has to be in their intersection. And this is how they prove theorem 1.2. They combine the wedges.
Right. The Euler-normalized genus is the distance between these wedges.
Imagine 2 V-shapes on a graph. If they're centered at the same spot, they overlap perfectly, and the bottom of the safe zone is at height 0. But if one is shifted relative to the other, if the signature and the upsilon invariant disagree, then the safe zone, the intersection, gets pushed up. Any valid surface must be high up enough to be in both wedges. That minimum required height is the Euler-normalized genus.
That concludes section 3. We've built the 4D framework. Have we unpacked it sufficiently?
I believe so. We've defined the 4D geography, established the signature bound and the upsilon bound, and showed how they can conspire to enforce a non-zero normalized genus. We're ready to compare 3D and 4D in Section 4.
Section 4, Euler-normalized genus agreements. We are looking at Section 4.1, alternating knots. They provide a combinatorial proof of theorem 1.3. A knot is alternating if and only if PM3K.
Right. For this, they go back to the state surfaces we talked about. They use the all-A surface, called 5A, and the all-B surface, 5A, that you can get from any diagram.
And they start with Euler's characteristic formula for a sphere. The equation is $2 is less than CR plus SA plus SB duh.
Or 2 equals negative CR plus the cardinality of SA plus the cardinality of SB. Here, $2 is the number of crossings, and SA is the number of circles in the all-A state.
From this simple counting formula, they derive that the gamma plus FA equals $, capital gamma plus of FA equals 0.
It's a really beautiful algebraic manipulation. They just plug all the counts of circles and crossings into the big definition of gamma. They use a known formula for the signature of alternating knots, and everything just cancels out perfectly to 0. It's like a checksum that passes, proving that for alternating knots, this special all-A surface sits exactly on the boundary of the wedge.
They also offer a topological proof using a result by Joshua Green.
Right. Green proved that alternating knots are the only knots that bound both what are called positive definite and negative definite surfaces. And a definite surface is one that, in this new language, corresponds to a point where the Euler-normalized genus is 0. So if your knot has both kinds of these optimal surfaces, it must be alternating. It connects their new genus to a very deep theorem in knot theory.
Does that cover section 4.1?
Yes. Both the combinatorial and topological proofs confirm that having an Euler-normalized genus of 0 is the signature of being an alternating knot. Let's move to the Turayev genus.
Section 4.2, Turayev genus. They define the Turayev surface 50 stars, and the formula for its genus is GATD fra 1 2 CR plus 2 SA SBR.
That's GT of D equals 1/2 times the quantity. CR plus 2 minus magnitude SA minus magnitude SB. This really measures how deficient a diagram is compared to being a planar graph. It quantifies how non-alternating it is.
And theorem 1.4 states, gamma 3K,
where gamma 3 of K is less than or equal to GT of K. This is an important bound. It says the actual topological complexity, the non-orientable 3 genus, is always less than or equal to this Turayev genus calculated from a diagram. The Turayev genus acts as a ceiling.
And they also mention conjecture 1.6. For adequate knots, they're equal.
Right. Adequate is a specific technical property of a knot diagram related to how the state circles behave. This conjecture suggests that for a very broad and important class of knots, the Turayev genus is the non-orientable genus. The diagram tells you everything you need to know about the minimal surface.
Is that sufficient for 4.2?
Yes. We've established the inequality and the conjecture. Let's look at the torus knots in 4.3.
Section 4.3, torus knots examples. They focus on the torus knots, $3. They analyze their proposition 4.5. And the result is that while a plus 3 equals 0, but 15 Fagari 3 equals 3 equals 0, but Vegat 3 canis 3 equals 2.
This is a striking asymmetry. The positive Euler-normalized genus is 0, which means there is a surface that touches the positive side of the signature wedge. But the negative one is 2, which means there's a gap. The most efficient surface on that side is still 2 units of complexity away from the theoretical minimum.
So it captures the handedness of the knot.
It does. It shows these invariants can detect the chirality and asymmetry of the knot structure. One side is perfectly optimized, the other is deficient.
That concludes section 4. Have we missed any nuances?
We've covered alternating knots, the Turayev genus, and the asymmetry of the T4 $3 knot. We are ready to discuss gaps in section 5.
Section 5. Ordinary genus gaps, pretzel knots. The setup is clear. We want a knot where the 3 genus is huge, but the 4 genus is tiny. They use a specific family of pretzel knots like PK, R, mash R1 dots.
Right. A pretzel knot is defined by these columns of twists. So PKRR1 means one stack of man twists, one of twine twists, and one of twi1 twists, all braided together.
And proposition 1.7 claims 2 things. First, that gamma 4p equal 1 in gamma 4 of p equals 1, and second, that gamma 3p equals 2 emma 3 of p equals 2n.
Let's focus on that second part. The 3 genus, 2 $, can be made arbitrarily large just by adding more columns to the pretzel. The knot gets more and more complex in 3D.
But in 4D, it's always 1.
But in 4D, a gamma 4 is always just 1. It's a simple Möbius band. The reason is that they can use these things called band moves in 4D, specifically a type 2 move, which involves a non-orientable band.
So you can do surgery on the knot in 4D.
Exactly. You can perform a kind of surgery using a Möbius band to reduce this incredibly complicated pretzel knot all the way down to a trivial, unknotted circle. And that whole process takes place on a surface of complexity 1. The 4D space allows for a kind of wormhole shortcut, the band move, that just collapses all that 3D complexity.
They also calculate the signature. The formula is sigma p, or take O or 2, or take O 2 22.
That's sigma of p equals k minus r, a simple formula.
So the final result is the gap can be arbitrarily large.
This proves it. It shows that 4 space is vastly more efficient at unhanging these specific non-orientable surfaces than 3 spaces. The difference isn't just a little bit, it can be infinite.
Does that cover section 5?
We've defined the knot family and explained the mechanism of the gap using 4D band moves. Let's move to the Euler-normalized gaps.
Section 6, Euler-normalized genus gaps. The goal now is to find a gap in the Euler-normalized genus, which is theorem 1.8. They use the specific knot 1 pianist is P3, 3n's, for any odd $1 in Gek, 3 point.
Okay, so this is a very specific slice pretzel knot. And because it's slice, we know its 4D genus is simple. In fact, we know that 4D Euler-normalized genus is 0.
So the entire question is about the 3D version.
Right. Is the 3D version also 0? If it is, there's no gap. If it's not 0, we have a gap.
And to prove it's not 0, they pull out the big guns. They use essential surfaces and edge path systems, a theory developed by Hatcher and Ortel. This is section 6.1.
This is serious machinery. The idea is that you can decompose the space around the knot into a set of standard building blocks, these 3 balls, and inside each block, any essential surface looks like a simple saddle. Hatcher and Ortel showed you can describe how to glue these saddles together using paths on a 2D diagram.
So it's like a subway map for surfaces.
That's a great way to put it. They describe this edge path diagram with coordinates on V on the plane, math B by O2. The vertices, or stations on the map, are denoted by things like Langle P, Q, Gela bracket P over Q.
And these represent rational slopes.
Yes. A path on this diagram corresponds to a specific way of gluing the saddle pieces together, and a valid path creates a valid essential surface.
They define basic edge paths. The expression is sigma PM 1 PM 1 PM 1 PM.
Phonetically, sigma plus minus p equals angle bracket 0 connected to angle bracket plus minus 1 over p. This represents one of the simple twists in the surface that corresponds to a twist in the pretzel knot.
They distinguish 3 types of systems, type I, type 2, and type 3.
Right. Type 2 contains the familiar Seifert surface. Type 3 contains the state surfaces we saw earlier. Type I is the the weird stuff. It contains all the other more exotic candidate surfaces that don't fit the standard constructions. To prove their result, the authors have to check all of them.
Okay, does that set up the Hatcher-Ortel machinery sufficiently?
Yes. It's a powerful, combinatorial way to list every possible essential surface for this knot. Now we just need to compute their genera.
Section 6.2, computations. They define various parameters of the paths, length, sign, and twist, which they call tau of E, and they give a monster Euler characteristic formula for type I systems.
It looks formidable.
It is. The formula is lambda plus n frac 1 into 2.
That's chi of lambda over pound lambda equals negative magnitude lambda plus n minus the fraction. 1 over 1 minus u naught times n minus 2. But as scary as it looks, it's just a formula where you plug in the coordinates of the path.
And from xi, the Euler characteristic, you get the Betti number.
Exactly. So they run this calculation for all the possible paths of type 1, type 2, and type 3 for their chosen knot, PD18.
And the result. They show that for the weird ones, the type I surfaces, cola 2 capital gamma minus of lambda is greater than or equal to 3/2.
Right. And since the normalized genus has to be an integer, this implies the value is at least 2. They do similar calculations for type 2 and type 3 and find the minimum is also at least 2.
So they checked every possible candidate surface in 3D.
Every single one. And the best one, the minimum, has a normalized genus of 2.
But in 4D.
In 4D, as we said, it's 0. So we have our gap, HALO 3PN equal 2, but HALO 4PN equals $1.
A gap of 2.
That proves the gap exists even for the Euler-normalized genus. Does that cover section 6?
I believe so. We walked through the Hatcher-Ortel classification, saw the formula, and understood the final comparison. We've thoroughly unpacked section 6. Let's finish with connected sums. Section 7, connected sums. They start with lemma 7.1, which establishes additivity. The formula is gamma PMU K2O3 K0 plus het Kov high.
That's gamma hat plus minus 3 of K0 connected sum K1 equals. Now, this is more surprising than it looks.
Why is that?
Usually, genus-like invariants are subadditive. That means the genus of the sum is less than or equal to the sum of the parts. You might find a clever way to join them that actually saves some complexity.
But here it's strictly equal.
Here, they prove it's strictly additive. The complexity just adds up. Their proof is clever. They add twisted bands to one of the surfaces to match the Euler numbers, which allows them to use the known subadditivity of the ordinary genus in a very controlled way. It basically says, for this specific invariant, you can't cheat by combining knots.
And finally, this leads to theorem 1.9, the infinite gap. They take the knot Taichan Kia 2 equals the n-fold connected sum of P.
Right. They take knot copies of that pretzel knot we just analyzed and tie them together end to end.
And using the additivity we just proved, they derive the final result. Had gamma gas 4 Kn, 2 NFN.
That's gamma hat minus 3 of Kn minus gamma hat minus 4 of Kn equals 2n. The logic is simple.
Owen.
The 3D genus just adds up because of additivity. So you get $2 plus 2 plus dollars, which is $2 times, which is $2. But the 4D genus stays 0 because the connected sum of slice knots is still a slice knot. So the gap between them, $2, can be made as large as you want just by taking more copies.
So the difference between the 3D and 4D Euler-normalized genera can be arbitrarily large.
The worlds diverge completely.
That brings us to the end of the technical content of the paper. Does that cover section 7?
We have proven additivity and used it to show the infinite gap. We have completed the linear traversal of the paper.
Then let's move to the outro. To recap, we started by defining this new quantity, the Euler-normalized genus, a way to measure surface complexity that's stable against simple twisting.
Right, and we saw how it creates this geography on the Dmer grid constrained by these wedges from signature and upsilon.
We found that for the very special class of alternating knots, this new genus is precisely 0. It's a perfect detector.
And then we went to pretzel knots, and using the heavy machinery of edge path systems, we found a gap. A fundamental difference between the 3D complexity and the 4D complexity.
A gap which we then showed could be made infinitely large.
It's a remarkable journey through their argument. And it validates this idea that properties like adequacy and alternating are not just features of a drawing, they are deep topological properties that manifest as minimizing this genus in the actual three-dimensional space.
And I want to leave our listeners with the final provocative thought, which comes from the authors themselves. They state a conjecture that for adequate knots, the tri of genus, that quantity from the diagram, is exactly equal to the non-orientable 3 genus, the true topological minimum.
So the question is,
why would adequacy, a property of how you draw the knot on a piece of paper, control the topology of all possible spanning surfaces in 3D space.
And that really is the mystery. It suggests that the shadow of the knot, the diagram, contains far more information about the three-dimensional reality than we might intuitively expect. In some deep sense, the shadow controls the object.
And with that, the deep dive is complete. Thank you for listening.